that ICPIC in China, we had to synchronize with some trip schedule of the boat.
Yes.
No, it's not ICPIC. It's not ICPIC. I'm talking the other one, Isaac.
Yeah.
And so some of the conferences were actually put late in the year.
Yes.
So.
Yes, I do remember that. And yeah, that was a heck of a boat trip.
That is correct. But it was very enjoyable and very unusual conferencing.
Right. Uh-huh.
And it was Yangtze River, right?
That is correct.
Uh-huh. It was indeed. It was fun. It was interesting.
It really was. And when they were anchoring at various docks and we are getting out to the land and seeing some sightseeing places and then coming back, again, starting in the night, that was very interesting.
What I thought was particularly interesting, in some of the more crowded ports, they pulled up and you walked across many boats to get to the shore. Remember that?
Yeah. Mm-hmm.
That's apparently the way things were done there, are done there.
Right.
I like looking at this map that's up right now to see all the places I've been and the places I haven't been.
Oh, really? That's how it is color-coded? I mean, black and...
No. It's, the maps are in white.
Right.
That we're looking at. But just looking at it and seeing, huge areas of the world that I don't know anything about. I mean, I've been to the top of Africa and the bottom of Africa, but never to the middle. I've been to South Africa, Swaziland, and I've been to Egypt.
Right.
But nothing in the middle. Australia, I've been to a good part of the eastern half of the country, but I've never been past, going west. I've never been past, I think, Ballarat, which is not far from Melbourne.
We drove through the desert twice.
Did you?
That's right.
We flew
Nullarbor
to,
Desert.
We flew to Ayers Rock, and then we flew back from Ayers Rock. We drove up north from Cairns, as far north as the road went.
Yeah, that's interesting too. There.
Yeah. We went to a place called Cooktown. And then the road started to peter out, and they said you needed a 4-wheel drive to go past there.
Yeah, Cooktown is pretty much the end of it.
Yeah. But it was interesting. It was very interesting. I mean, what were the name of some of the places? Mossman up there, and Port Douglas. Then you came down to Palm Cove, which is just outside of Cairns.
Right.
So we're missing this season. One season of Big Pigs is missed.
But I gotta say, the most fascinating place I've ever been to, in a real sense, is down at the bottom of the map. You see this piece of Antarctica sticking out toward South America, right at the bottom. We took a trip there some years ago. It was
and it was cold.
It's always cold, but it wasn't as cold as it could be because it was summer there. We didn't go swimming, and the temperatures sometimes got above freezing, but that was fascinating.
Hey, Steve, Teresa just wants to say hi.
Well, I don't know where he is. Oh, there he is. Hello,
there he is.
Yes, you
Good
know
to
who
see
he
ya.
is.
Long time no see.
Yes. How are you?
Wherever you are.
Hello, Klaus. Oh, very nice to see you both. How are you?
There you go. Oh, there's Ravi.
Hi, Ravi. Good to see you too.
Happy birthday in a few days.
Thank you. Was it
That's what it's Steve's birthday.
Happy birthday to all those December birthdays.
Yeah.
December birthday people.
Good to see you all. Have a good conference. Good luck.
Thank you.
Thank
Okay. Happy talking. Happy physicking.
All right.
you.
She has to go to sleep, you know. She has to work early tomorrow morning. Somebody has to bring in the money.
I see. Well, we we are extremely lucky that we have jobs that don't go away, and we can teach, do everything from home. It's not quite as good. As a matter of fact, it's not near as good, but it's what we can do.
So did you guys run the entire semester online?
Absolutely.
GSU? Okay.
Yeah.
Well, we did.
In the middle of nowhere, boom, suddenly they said, you know, we had a different plan and they wanted to go to Thanksgiving, but then the game was over suddenly, and
Yes.
that's it.
Well, for us, it was a very well-planned schooling this time. They said that they're going to do F2F, and they wonderfully executed the whole thing with the help of the faculty members, even the students. They did very well, contact tracing, isolation, quarantine, and all the stuff. And everyone was very careful to maintain this because they knew that the other option is just stop going back to the computers. So we did a fairly good job.
You may have heard that Iowa, in some states, suddenly Iowa did really bad, you know, just a couple of weeks ago. And then, boom, that was it, you know. So in fact, I'm sitting downstairs, you know, so I gave one show. I think some of my students might be logged on, you know. I gave one show with this thing here behind me, and then kneeling in front of this desk. And so I said, well, that's it. So then now I did it like the, you know, the soccer games or whatever you have these days, right? So I did it from an empty stadium, you know. So I went to the lecture hall and just did the show, and that was it, you know. So
it's difficult talking to the screen. It's not the same.
Yeah,
but it's interesting. We learned a lot.
That's right. But I mean, some things work well, you know, like this, for example, you know, I couldn't.
This is incredible, I have to say.
Fantastic, you know, really very well. I mean, I had to log off. Unfortunately, this morning I had another meeting, so I could only do about half of the session, you know, but it seems to be going well, you know, so it's great.
Absolutely. It's
yeah, Zoom works well for this kind of activity. I don't like it for teaching. We're actually doing our labs face to face, but we're putting the students in clusters. So, you know, we've odd week and even week clusters, so we can sort of spatially separate them out and have them wear masks and all the rest of it, you know.
Well, the trouble here in Georgia in particular, we have a governor who does not allow individual municipalities to require masks. I mean, it is he is a Trump wannabe, but he's not quite so stupid and reckless as Trump, and so he's only a wannabe. But he has ordered the university system to have in face-to-face classes, and they just flatly refused. They said, no, we're not going to listen to the governor.
No.
It's kind of like
risky.
Like the Nuremberg trial rules that I was only following orders doesn't work. So we're not following orders.
But now Trump hates your governor the most.
Yes. Also, the governor of the Republican governor of Arizona.
That is correct.
They wouldn't overturn the election for him.
Yeah.
What kind of loyalty is that, I ask you? And then he appointed Supreme Court justices, 3 of them, and none of them would find for him. It reminds me of something that happened in history back in the 19th century. There was the Austro-Hungarian Empire, and in 1848, Hungary revolted, and it was put down by the Tsar of Russia. Tsar, I guess it was Alexander, I think think it was Alexander III, but I'm not positive. But anyway, Bismarck was very worried about that. He was, well, Prussia, but Germany. And he called in the Austrian foreign minister. He says, aren't you going to owe the Russians something? And the Austrian foreign minister apparently said, the magnitude of our ingratitude shall be legendary. And so the alliance remained between, I mean, because there was a loose reliance between them. It was called the Drei Kaiser League, the three Emperor League. Although Bismarck wasn't the emperor, Frederick was, but Bismarck was the troublemaker. Yeah. I've always liked that story. The magnitude of our ingratitude shall be legendary.
Yeah.
Well, we're seeing a lot of that now.
So it was, Steve, with the state of Georgia.
2 minutes before the session start, maybe, Ravi, can you just start sharing your screen?
Okay. Can you see a blank?
Anatoli, the other thing that is good is if you ask people to switch off their mics.
I will do.
I do that.
Absolutely.
I just watched the whole YouTube broadcast of the previous session, so I learned all the tricks.
Okay.
That's
can
right.
you see my screen?
No, not yet.
Do you see my screen?
No, not yet.
Oh.
Hey, John.
There's a green button at the bottom, share screen, right at the bottom.
Right.
Oh, I can do that. Do you see me?
Not, yeah, someone is, yeah, that's
Now
Ravi.
There it is.
Good.
There it
Okay,
is.
good.
Yeah.
Good.
It would be great, and then probably.
Hey, Steve, you look like you're right off the set of Annie Hall there. Is that 70s?
Yeah, we are almost ready, I think, in less than a minute.
I think this is Alfred's screen.
Right.
Hey, Himadri.
Yes.
This is Alfred's screen.
You want me to share?
I thought I was sharing.
Yeah, you were sharing already.
Yeah.
So
Okay.
let me just quickly do it. Just make sure that I'm okay. Can you guys see my screen, Anatoli?
Yes.
I can see it.
Yes, yes.
Yeah, I see you now.
All right.
Good.
I
So,
can see everybody.
yeah. So, Anatoli, I think we are good to go.
Yes, it's 3
So-
o'clock.
Yes. So, greetings, everybody, and welcome to the second session of this conference. We had a great session yesterday, which really went very well. And today's session 2 will be chaired by Professor Anatoli Kheifets. And Anatoli is an expert on quantum many-body theory, Green's functions, Feynman diagrams, with great contributions to atomic electron-atom collisions, photoionization processes, electron momentum spectroscopy. So it's really great to have Anatoli to chair today's session. And the co-chair will be Professor Thomas Gorsica, who you have all met yesterday already. So Anatoli, please take over.
Okay, thank you very much, Pranava, and I'm deeply honored to chair this session and in celebration of Steve Menson's long lifetime achievements in atomic physics. He's one of the founding fathers of modern atomic physics, and we learn from his books and articles. And I'm extremely happy to join Steve in the past decade, and we worked together on time-resolved atomic processes. And it was great fun, I hope, for both of us. And please let me introduce our first speaker, who will be Professor Ravi Rao from Louisiana State University. And he's also one of the founding fathers of atomic physics. And his talk will be of energy and time resolution in atomic processes. Please, Ravi.
Okay, thank you. So can you see my screen now?
Absolutely.
Right.
Yes.
Very good.
Let me get my
Well,
cursor.
before you start,
Okay.
Ravi, can I please ask everybody to mute microphones just to reduce background noise?
Right. Well, greetings to everybody. And of course, I'm sorry for some of our European colleagues who are even later into the night in the very early hours. But greetings to everyone. And my thanks to the organizers of this symposium for including me in this, because it's a real privilege to be able to speak in honor of Steve. Happy birthday, Steve. And to because Steve Manson is my oldest friend and colleague in the field. I met him soon after coming in 1966 as a PhD student to the US, and he was a postdoc with John Cooper. And we met fairly a couple of months after. And from that time on, actually, we have discussed photoabsorption in atoms and molecules. So going back to 1966, mostly atoms, of course. So it's a great pleasure, personal pleasure for me to talk here in this session. Now I'll start my slides with this first slide. This is a little later than 1966. This was a photograph in 1974 in Ugo Fano's office at the University of Chicago. We had gathered there for an APS meeting, and you'll see John Cooper, Fano, and Joe Masick. Can you follow my cursor in the front row? And Steve Manson standing behind Fano. So there you see Steve. And among the others here, this is Tunan Chang, who was a postdoc at that time. He's also going to be speaking in this symposium in session 4. And Tony Starres and I were former students who had come to the Chicago meeting. And the current students at that time, you'll see in the back, Chidong Ling, Giancarlo Strinati, Kostas Theodosiou, and Jiaming Li. So this is an early photograph of Steve in Chicago in '74. So let me talk about energy and time, because what quantum physics brought into physics was the idea of these conjugate pairs of quantities. And for today's talk, it'll be energy and time. And what that does is allow us to use either as a representation. So just like we talk of position and momentum representation, we can do everything in the energy representation or in the time representation and get at the same physics. So if you think about the energy side, then of course we are dealing with the time-independent stationary states of the Schrödinger equation, the time-independent Schrödinger equation. We're talking about energy eigenstates, whether they are bound states or scattering states, and we're talking about standing waves for the most part. So on the theoretical side and the description, and on the experimental side, you're talking about very high resolution energy spectroscopy. So of course, in the 60s with the advent of synchrotrons, and then later with lasers and multiple lasers, higher and higher energy resolution. And this was sort of the driving force in the development of atomic physics. So photoabsorption, which will be the main theme for my talk today, and things like angular distribution, the Cooper minimum. You'll hear more about Cooper. You just saw a picture of John Cooper. In fact, let me go back a minute to that. Somehow it's not allowing me to go to the previous slide. But let's see if I can get to the next. Somehow this is, I don't seem to be able to go back to the previous slide. There we go. So this is John Cooper. And both John Cooper and Tony Starres, unfortunately, we have lost recently. John died in August and Tony about a little over a year ago. So coming back, we're going to talk about the Cooper minimum. And you can bring back time into the description through the famous Wigner time delay, the Wigner, Eisenbud, Felix Smith expression. And I'm going to talk about these things. and in particular highlight it with a recent paper in which Steve Manson and actually 2 of our organizers were involved in that. And I'm going to talk about that for the energy side of the equation. Now, of course, when we talk about the time representation, we're going to be looking at the time-dependent Schrodinger equation. And you can actually now, with computers, basically start with a wave packet and directly integrate out. And many people do that, including, for instance, my colleague Ken Schaefer and Mette Garde in my department. So the theory side is because of that capability that we have. On the experimental side, of course, it's the development of shorter and shorter pulses. So you can get to very accurate time measurements, femtoseconds, attoseconds, and so on. So of course, there are pump probe experiments. And then I'm going to highlight one particular thing today, which is the delayed photoemission. And it's an experiment which was done by a German group of Pfeiffer, Heinzmann, and their collaborators in tungsten selenide. So let's go on to talk of the Cooper minimum. Now, we call that the Cooper minimum. It has an earlier history. It was actually experimentally observed first by Ditchburn and then theoretical work by Bates and Seaton. But it was Cooper who really systematically analyzed when one gets these Cooper minima and came up with some basic rules. And so this is how it has come to be called the Cooper minimum. And the Cooper minimum is something which I'll give you a very little feel for it, but the experiment, the theoretical paper and some of the experiments I'll refer to are in the photodetachment of the negative ion chlorine or the photoionization of argon, going of course to the neutral or the ion plus the electron. Now you're starting with a p electron, you'll go out either as an s or a d electron because of the photoabsorption. So of course, near threshold, there will be the threshold laws. So for the negative ion, this is the famous Wigner threshold law, that the cross section will depend on the L value of the outgoing electron. So of course the S wave dominates and to this energy power. Whereas for, of course, the Coulomb system, because you have a Coulomb field, which is much longer in range than the angular momentum, that dominates, and then you get a constant. And again, angular momentum is irrelevant, so all partial waves are on the same footing, near constant. And there is a time delay, which is then defined in terms of the derivative of the phase shift with respect to energy. Of course, it could be an advance if the phase shift is falling, so this derivative is negative. Now, to get a feel, for instance, for the kind of numbers we talk about, so if you think, for instance, particularly of time advance, you have to go in of the order of an A0 and come out, so there is 2A0 with some velocity, and so that is, of course, going to be related to this constant, and that's 10 to the minus half angstrom, 10 to the minus 8 in the numerator, 3 times 10 to the 10 centimeters per second. So you get numbers of the order, as you see here, in the few tens or about up to 100 attoseconds. So it is really the advent of attosecond spectroscopy that allows some of the experiments that I'm going to talk about. Now, there's also a Wigner cusp near the threshold. And let me just explain a little bit about the Cooper minimum first. Ignore this for the time being, I'll come back to it. But the systematics of the Cooper minima are actually quite nice to state in terms of simple hydrogen orbitals. So of course, for instance, here we are talking of a P going to a D. Incidentally, that's one of the first rules of Cooper's. You have to go from to L plus 1. And so if you are thinking of the 3P and the 3D radial wave functions, then at low energies, since we always define things as positive as they start out, the dipole matrix element is always positive. But later on, even the continuum electron D, of course, at small distances and medium distances, will look something like this. And so you see that dominantly it becomes negative. So the dipole matrix element goes through a negative, and that means it goes through a 0, and that is the reason for the Cooper minimum. And here is the paper of Manson, Kheifets, Deschmuck, and collaborators. So on the left side, you see the chlorine minus and the argon, the cross sections. And of course, chlorine minus starts out much smaller near threshold. And whereas the Coulomb threshold, the argon starts much higher. But the minimum that we are going to talk about is here around about, say, 45 electron volts, whether in chlorine minus or argon, and that is the Cooper minimum that we will talk about. And of course, if you look at the dipole matrix element, there are various thresholds for the various subshells. And if you look at the dipole matrix elements, you see here the 0. And so whether it's in chlorine system, the chlorine minus or the argon. Now, if you look therefore in the vicinity of the minimum, incidentally, there are many things you would expect. Non-dipole effects, maybe quadrupole and so on are also of interest. But in particular, let's look at the phase shift. And again, around that 45 volts, whether it's in chlorine minus or argon, you see a big change. And so this is, of course, much more, stands out much more than even in the cross-section or the matrix element. And then the derivative, which is the time delay. So you see these structures, and both in chlorine minus and argon. And notice that the time delay here is negative, and so also into this region here. And so most of this is actually a time advance, if you wish, in the negative ion system. And so these are the calculations done by a relativistic random phase by Manson and collaborators. And it shows very well the idea that around the Cooper minimum, things like the time delay are actually even more sensitive parameters for examining what is going on with the cross-section. Now, let me change ground a little bit. And so now I'll talk about the two-valley potential, which will figure for the rest of this talk. And what it is actually very interesting and very simple. And these all became possible in 1963. So Cooper, Steve Manson and I and so on are very associated with the early days, because Hermann Skillman had come out with these tables of potentials and wave functions across the periodic table. And they were Hartree-Fock calculations with a Slater exchange. So you could talk of a kind of VFR. And basically, some of my early work was simply to take these Hermann Skillman potentials, add the angular momentum, and then you get these very interesting structures. And the way to make sense of it is that if you imagine you're on the photoelectron, you're riding out from small r to large r, then very close to the origin, of course, you're seeing the full charge minus z e squared over r as your potential. Of course, very far away, most of it is screened, and you're seeing a minus e squared over r. So in a certain sense, therefore, in between, it's falling off even more rapidly than 1 over r. And actually, it's very well mocked by roughly a 1 over r squared fall off. And therefore, if you now add the angular momentum potential, which also is a 1 over r squared, which is, of course, purely repulsive, then you can get this idea that for sufficiently large L, and depending on the Z values and so on, you could actually get a barrier in between barrier region and form a two valleys. Now, clearly, this is going to have an enormous effect on very low energy electrons. So if I think of a photoelectron, say, for instance, from either the 4s or the 3D shell, in particular the 3D shell, if you pop it up into the F outgoing wave and you're just near threshold, it's of course going to have to tunnel through this barrier, and that adds a particular delay. And what is remarkable is that these things that we talked about, maybe I'll show you, this was actually my early plots on graph paper. This is in June 1967, when I was just beginning with Professor Fano in Chicago. And I took the Hermann Skillman potentials and added the angular momentum. And there's a lot of interesting atomic physics you can see in these barriers. So for instance, if you look at this, it's a little probably dimmer for you to see, but the 18 is the argon, and there is a barrier there. And then of course the barrier drops. And so scandium, which is 21, there is no barrier. And that is of course the reason the d electrons start going in. And from 21 up to 29, there is a drop, and therefore the copper, so the transition elements fill in into the inner part of the region. And then the barrier builds again at the higher Z values. Now the same thing happens, of course, for the F wave. So this is L equal to 3. And again, you see 54 is xenon. There are no F electrons still, but 57 up to 71, which is the lanthanides, there are the F electrons coming in. And this particular experiment, incidentally, this was the paper in which we talked about this, But what is interesting now is about 50, 60 years later, technology allows the measurement of something like this. And this is indeed what is measured by this German group of the delay in the D shell ionization coming out as an F wave compared to the P wave coming out from the 3D or the 4S, and the delays that they measured of the order of 20 to 40. I think I have just a few minutes, so let me just talk about what might be further things that one can look at. We talked about an energy representation or a frequency and a time, which are of course Fourier conjugates even before quantum physics. But we can think in terms of a mixed representation where you have a control in a sense of both. Now, actually, this also goes back a long way. In fact, if you think about Western musical notation, it is a mixed notation. You have the pitches denoted on the bars, and then there are the time intervals laid out. So this is, for instance, one of the canons of Bach. And so this is something which has a long history in a sense, goes back centuries. And in physics, Denis Gabor, already in the 40s, had talked about the use of wavelets. And it has been, of course, stretched a lot more by, again, French mathematicians, Daubechy and others. And so the idea of using wavelets as a way of, say, increasing convergence, speeding up convergence. And there are similar things in atomic calculations when we talk about B-splines and so on as bases in computation. And the idea of either a time representation or a frequency representation catching the same physics is, of course, something which, again, has a very large coverage. So, for instance, when we talk about the life cycle of a star, instead of being able to look at it in a time sequence, which is incompatible with our own lifetimes, you can just take a snapshot at some time of millions of stars at various stages of evolution. This is what our astronomy colleagues and friends do. Or I want to show a very interesting painting, which goes way back to a German woman painter, Maria Sibylla Merian, who at that time was painting things like this, which is completely different from all the rest, the Caravaggio's and so on. And in particular, that she was doing things like insects. Insects were actually not considered sort of good for paintings. You either did Bible stories or landscapes and so on. Insects were of the dirt, and they were, if at least ugly, if not evil. And but what she was doing today, of course, we do botanical and zoological illustrations. But here you see, of course, the full life cycle captured. Whereas today's technology, you could actually start from the egg and, with high-speed photography and stroboscopic photography and all that, actually follow the time sequence of going through the caterpillar and then the pupa to the butterfly. So, yes, I'm almost done. And so both high energy resolution and time dependence, of course, being combined, we are seeing now being explored. Again, it's because of what technology allows us to do. And let me end, therefore, by connecting this back to our mentors of Steve's and mine, of Fano and Cooper, who used to emphasize the role that technology plays in the development of science. We usually think about science, of course, leading to technologies, but it is really the technologies, whether it's a synchrotron or lasers, or in this case, as I said, time spectroscopy, which allows certain kinds of science to sort of flourish. So with that, let me stop and thank you for your attention. And again, a happy birthday to Steve.
Thank you very much. Right, it's very inspiring talk and lots of nice analogies and beauties. Unfortunately, we don't have much time for questions. So guests are encouraged to use the chat box. They can place their questions in chat box and then we pass it on to the speaker. And in the meantime, we invite the next speaker, who is Professor Chris Greene from Purdue University in Indiana, and he will be talking about Fano line shape physics in the time domain. Thank you. I ask everyone to mute the mics except the speaker because we still hear some background noise.
Let's see. I think it's not showing the right display. Do I have to go to full screen before I go to before I begin sharing?
I think so. No, you are in a presenter mode. In presenter mode, you see all these little things.
Switch to slideshow mode, sir.
If you just switch off presenter mode and go to the plain mode of PowerPoint, then share it, then we will see.
Use the wine glass icon.
Wine glass. I don't see a wine glass.
Yeah, I think, Chris, you should probably go to share screen before you get onto. I mean, you go to full thing
before I
go to the share screen, then bring up the PowerPoint and then wine glass.
Right.
Okay, let me try that. Share screen first, you say?
Yep. Then choose the PowerPoint screen.
All right. Yes.
And then the display. Yes, now go down to the wine glass, right in the bottom right, there is a wine glass.
Bottom right.
Is that what you call the wine glass? No,
yeah, just before bottom right, not left. Go to the right.
Oh, bottom right.
Yeah.
Wine glass.
It's on the PowerPoint window.
PowerPoint window at the bottom right, just by your sound slider.
Yeah, that's where I always go. Okay.
But you are in
on the top, click on display settings. Go to display settings.
All right.
Duplicate slide.
Swap presenter view and slideshow.
Duplicate. Yeah.
Okay.
Yeah. Thank you.
Okay. Sure. So yeah, sorry for that confusion. I haven't given many talks this way in Zoom. So what I wanted to cover today was this subject about what is, if you take one of Ugo Fano's line shapes that we're so used to, very asymmetric typically in the frequency domain, and you look at the corresponding time domain physics associated with it. And this is in some sense an old topic, but in another sense, there was a comparatively recent insight that I think emerged at around the time of our 2013 Science article that I collaborated with Christian Ott, who is a PhD thesis of Thomas Pfeiffer. And there were other theorists and experimentalists involved who are listed here. We then followed up on that basic investigation, which combined both theory and experiment, with a follow-up 2017 PRA article with a PhD student in my group, Bin Yan, who's now a postdoc at Los Alamos. And this work was supported by DOE. Before I get into that, though, I need to say a little about Steve. First of all, there was a time in the 1980s when I was really unhappy with a lot of experimentalists that insisted on doing experiments in photo absorption of the valence shell of strontium and barium, which looked like a hopelessly impossible task to ever develop theory to describe those experiments. Just too complicated, all these doubly excited states and infinite Rydberg series and perturbers. And it just didn't seem like our matrix technology could ever really get to describe those. And so toward the late 1980s and early 1990s, when a collaboration with Mireille Aymar began to show promise and started to produce spectra theory and experiment agreement, like this example in strontium photoabsorption, where you started to think the theory was actually kind of nailing it. I was, very, very pleased with this. And I would go up to Steve Manson at conferences and try to show him my graphs and try to get him excited. And I could always count on him to kind of burst my bubble and say, but where's the physics? What's going on? What's the dynamics? What are the configurations? And so Steve was always really pushing me, and I value that really, although it also kind of burst my bubble at the time. But that's kind of characteristic of Steve, always pressing deeper and deeper on physics points. So back to Fano line shapes. A lot of what I learned about them was, of course, Fano's 1961 paper, but also the famous Review of Modern Physics article by Fano and Cooper. And while that focused primarily on the frequency domain, I did go back and try to see what Fano and Cooper were saying about time domain physics. And actually they had some comments about time domain physics, how one could look at the how the electric dipole moment of an atom would vary in time after an initial disturbance. And you could imagine applying an impulsive displacement to all the atomic electrons initially, and then look at the mean oscillating dipole moment at later times. And this is a quote from that paper, that then the frequency spectrum or Fourier transform would be the oscillator strength spectrum. So they were already thinking a bit in terms of these time domain implications, but in hindsight, it's a little surprising that they didn't pull out a simple result that came out rather simply in the end in this collaboration that led to this science paper in 2013 with the Thomas Pfeiffer group, which has already been getting quite a few citations, although we are quite a ways behind Fano's paper, which is nearing 9,000 as of today. So let me try to go through briefly the theory of this. The basic idea of the theory of that paper is simply what we teach our E&M graduate students when we teach them, like the Jackson course, Kramers-Kronig analysis. And basically, in the case of a Fano line shape, which looks like this in the frequency domain, which is, of course, proportional to the imaginary part of the dielectric constant, then the Kramers-Kronig relation tells us what the real part of the dielectric constant. We just have to do this principal value integral over the imaginary part. And that's a pretty straightforward integral to do. Well, there's a couple of tricks, because you can have divergences that you might have to regularize, but sweeping that kind of math under the rug for this talk, then in the end, you can make the time-dependent dipole by then transforming back the full complex dipole moment. Now, what you get when you do that is this simple thing if you do an impulsive excitation. So hit the atom sharply at time 0 with a very sharp laser pulse, and that sets in motion a dipole oscillating, which decays also. This is an autoionizing resonance, so it has its decay to the continuum, represented by this exponential factor. But the Kramers-Kronig analysis gives this factor Q minus I squared, which tells you that the phase, if I rewrite that Q minus I squared as an amplitude, Q squared plus 1 times a phase factor e to the I5Q, tells you that the Fano line shape Q parameter in the frequency domain tells you the phase of these dipole oscillations. And that's the key relationship that was so simple, I could hardly believe that this had not been derived before. And in fact, there were hints of it certainly in previous literature that I'll mention later. But in any case, the Pfeiffer group really grabbed this idea and did some pretty interesting physics with it, some interesting experiments. So for instance, they showed how the phase after a dipole excitation would change. This is a cartoon figure. The phase of the oscillating dipole is on the right after an impulsive excitation at time 0, and how that phase is changing depending on what the line shape looks like. There is maybe more interesting to look at some real data from that science paper experiment that the Pfeiffer group carried out, like for the famous doubly excited states of helium, where you have the clear asymmetric Fano profiles in the frequency or energy domain, that then they can look at in the time domain as well, those same resonances with an impulsive laser excitation. And one of the remarkable things, the really clever idea of the Pfeiffer group was that they could turn that backwards or turn it around. They could impart an extra phase by bringing in an infrared laser pulse and change that phase and then change the Fano line shape of the absorption spectrum. So here in this case of the doubly excited singlet p-odd series in helium, then after this laser pulse, they could change those asymmetric profiles in the photoabsorption spectrum. Strictly speaking, it's this optical density absorbance measurement, but they could change that into a Lorentzian type profile because they've changed the phase of those oscillating dipoles. And similarly, they could start with Lorentzians in the bound spectrum here on the right, and they could do this impulsive extra infrared laser pulse and change those into asymmetric Fano line shapes. So, and there are other examples. These are cases where they changed the phase. Here where they imparted 0 phase, it looks like the original spectrum. They could change it with a phase imparted of 43 degrees into a Lorentz, or they could make them window resonances and so on. They really, by this method, they can modify the absorption line shapes, the Q parameter of the Fano line shapes, basically. So what we did to try to understand this further, one of our questions was, how general is this phase to Q parameter relationship? In particular, does it hold to other excitation operators, other transition operators, or is it only really through this Kramers-Kronig analysis, which seemed unlikely, but we really wanted to look at it in a simple model. So we looked at a Feshbach resonance model of the square well type, the kind of basic thing everybody would do. And by changing the parameters, we can go from a window resonance to a Lorentzian peak to asymmetric Fano line shapes with finite Q parameters. And so basically in this study, we were able to verify that it's the same kind of Q relationship as we varied the transition excitation moments to the closed versus the open channel. We could change the line shape of the Q parameter shown in this graph, and we could see the corresponding phase change in the dipole, or I should say the transition state, evolving, oscillating in time once you impulsively excited that resonance. And if we plot the phase shift versus the Q parameter as shown in the bottom here, it does confirm this phi relationship to Q. And this is just a larger version of that. I don't need to dwell on that. So this does seem to be a rather general phenomenon, and let me maybe just touch a little bit on the more general literature. One thing I found interesting was this recent paper by the birthday boy and several others in this audience here, that they were looking at time delay, photoionization time delay in the vicinity of Fano resonances, and could see this same factor Q minus I showing up prominently. Actually, I have a question about this for the authors maybe one day. because I would have expected there's a different Q parameter for the different channels, 2P to continuum D versus continuum S. So I wasn't real sure I understood the theory very well, but I haven't read the paper real carefully. I might have missed something. Also, there's been other important work on time-resolved phonoresonances and looking at the phonoresonance in the time domain by Qidong Lin, Joachim Bergdorfer, and experimental collaborators. Also, Marlene Wickenhauser was a joint student of Joachim and Qidong, and she had a really nice thesis on this subject. And they found expressions like this with, again, Q minus I squared times the oscillating excitation part. So the bottom line I wanted to stress was that Ugo's legacy does live on. It's getting 300 citations a year still. It's used in so many areas of physics, which is pretty interesting. That especially Fano told me once as a grad student that he felt this theory was obsolescent. But it is a really simple way to encapsulate a lot of physics. And since today is a very there's an election being settled, and who gets the most votes is sometimes declared the winner. Well, we're only 8,994 citations behind the Fano, but we think we've won, and I'm declaring it so. So anyway, happy birthday, Steve. I'm really glad to be here and participate in this celebration. You've done so much physics in your career. The end.
Okay, thank you very much, Chris, and wonderful talk. We wish you luck in catching up with Fano. And Fano's paper is the highest cited paper in atomic physics ever. So you're in a good competition. Now, we are a little bit behind the schedule, so the question arrangement is the same. If you have questions, please use the chat box and we pass it on to the speakers. And now let me please introduce our next speaker, who will be the group leader from Riken Institute in Tokyo, Katsumi Midorikawa. And we are humble theorists, and now I have the special pleasure of introducing an experimentalist, and he will show us how to produce, how transform gigawatts of laser power to petawatts by just compressing them in time. Thank you.
Okay, can you see my slide?
Yes.
Okay. So first of all, I'd like to thank organizer for giving me an opportunity to talk this conference. But I'm not atomic physics. I'm a laser physics. So in this talk, I will show you the state of art of laser technology. So the title of my talk is Generation of Gigawatt plus Isolated Attosecond Pulses by High Energy Optical Waveform Synthesizer. Okay, this is the content of my talk. After introduction, I will describe why do we need optical waveform synthesizer. Next, I show you high energy 3-color synthesizer newly developed in our laboratory. Then I will talk about the generation of very high intense isolated attosecond pulse by using this synthesizer. Next, I will show you how to extend the cutoff of attosecond pulses to the water window region. And finally, I will summarize my talk. So we have successfully generated intense attosecond pulse and used to investigate ultrafast atomic and molecular process. But the wavelength region well available is limited below 100 eV region. Beyond that, and intensity of attosecond pulse become quite low. So our next target is to extend intense attosecond pulses to the much shorter wavelength region. As you know, for generating short wavelength high harmonics, longer wavelength pumping has an advantage due to this equation. But disadvantage is when we increase the wavelength of the pump laser, photon yield of the high harmonics rapidly decreases in proportional to the pump wavelength to the -6 or -5. So we need high energy long wavelength laser for generating intense attosecond pulse in the soft X-ray region. But the low conversion efficiency is still a big issue. So in order to improve conversion efficiency, the use of optimum waveform, that means the optimum electric field, is important. The use of multi-color laser to increase the efficiency was proposed by several groups. This is proposed by John Malonga's group in Imperial College. This is our result, and this is proposed by Chindori group. Anyway, generation efficiency of harmonics are expected to increase 2 or 3 order magnitude by introducing optimum optical field. So next, I will show you how to create such an optimum waveform. Okay, several years ago, we proposed and demonstrated generation of the gigawatt class intense attosecond pulses by 2-color light field synthesis. Usually, generation of isolated attosecond pulses require few cycles CP stabilized laser pulse, but it's difficult to increase an output energy of such a ultra short few cycle pulse. But in our scheme, we use conventional multi-cycle pulses, typically 30 frames per second laser, like this. When we focus this multi-cycle laser pulse to atom and molecule, ionization occurs above the threshold, and train of attosecond pulse is obtained like this. For the generation of single isolated attosecond pulse, we need 5 frames per second pulse. But as I mentioned, it's difficult to increase the output energy of this 5 frames per second. So in our scheme, we use the supplementary pulse. The intensity is 1/10 of the 30 frames per second. Wavelength is but still a little bit longer, 1.3. At this moment, the synthesized field become like this. Near the central part, intensity distribution of the synthesized pulse is almost same as the 5 frames per second laser, so that we can obtain a single isolated attosecond pulse using multi-cycle pulses like this. This is an experimental result. When we use the single pump, 1 color, we could obtain the cone-like structure like this. But when we change to the 2 color, you can see the generation of strong peak here. This indicates the generation of isolated attosecond pulse. By using this method, we have obtained output energy of the 1.3 microjoule with a pulse duration of 500 attosecond. That corresponds to the peak power of 2.6 gigawatt. But this method has some disadvantage. One is you can see the generation of satellite pulse. This satellite pulse is generated, these satellite pulse of the pump. And at this time, we did not use a CP stabilization because of our laser is 10 Hertz and high energy. So that the peak intensity of isolated attosecond pulse fluctuates shot by shot due to the fluctuation of CP. So next target is realization, full stabilization of this isolated attosecond pulse by using this time the 3-color synthesizer with precise CP phase and relative time control. Okay, this is a photograph of multi-terawatt 3-color optical synthesizer developed in a laboratory for studying of the attosecond physics. We start the oscillator, regen, and multi-pulse amplifier. This generates the joule class output with 10 Hertz. After compression, our pattern of the beam are used for the generation of 2-color mid-IR pulse. And the total 3-color combined at the end of the setup and sent to the beam next door to generate isolated attosecond pulses. Okay, this equation describes the electric field of the 3-color synthesizer, pump, signal, and idler. These tau are the pulse duration of the pump, signal, and idler. Phi CP is the CP of the pump, and delta T and delta T2 are the delay between the signal and the pump and signal and idle. Total energy of this 3-color synthesizer was 54 millijoule, consisting of the 44 millijoule pump and 6 millijoule signal and 4 millijoule idle. The pulse duration of the pump was 30 femtosecond and the signal was 44 femtosecond, and the idler is 80 femtosecond. Okay, this is a schematic of 3-color synthesizer. The main pump pulse is CP stabilized 10 Hertz 150 millijoule Thai sulfur air. This laser is CP stabilized by a technique developed in our laboratory. And in order to stabilize this long optical path, we have used the Mach-Zehnder interferometer technique with visible CW laser. And because of the 10 Hertz high energy laser, short energy fluctuation caused the space-temporal coupling of the generation of the white light field. So to compensate such a jitter, we used balanced optical cross-correlator technique. If you have interest in this technique, please refer to these papers. And finally, we successfully stabilized the beam passes and energy fluctuation using this technique. Okay, so this is a summary of our synthesizer. Both CP and delay jitter are well stabilized using the technique I showed you. And in addition to temporal stabilization, beam pointing stability of 3 beam is also essential for this kind of the experiment. So we introduced a beam pointing stabilizer to stabilize the beam pointing and obtained this result. These values are sufficient for stable operation of 3-color pulses. Okay, these are the simulated, calculated synthesized field. The left figure shows the synthesized electric field waveform. Blue curve is the synthesized field, other signal, idler, and pump. And light is the instantaneous intensity profile of the pump and synthesized field. This pump is typical 30 frames per second pulse intensity distribution. But you can see the strong peak when we use the synthesized field. The intensity ratio between the central, this main peak, and closest near neighbor pulse is improved from the 1.02 to 2.1. This value is the almost same as the 2.5 frames per second at 800 nanometer. That corresponds to the almost single cycle. So we could generate the almost single cycle pulse for the generation of the high harmonic using the multi-cycle pulses. Okay, so this is a spectrum measure the single shot experiment. When we use a single one color pump, we could obtain the typical harmonic distribution, common-like distribution. This common-like distribution indicates the generation of train of attosecond pulse. But when we use a two-color, you can see the continuum-like structure and increase of the intensity in the cutoff region. But you can see the still small modification in this area that creates the satellite pulses. But when we use a 3-color, we can completely eliminate these small modulation and obtain the smooth continuum radiation. By Fourier transformation of this region of spectrum, we have obtained this temporal pulse with a pulse duration of 170 attoseconds and without any satellite pulses. The total output energy of this continuum spectrum is 0.24 microjoule, and the pulse duration was 170 attoseconds, so that the corresponding peak power is 1.4 gigawatt was obtained with a conversion efficiency of the 5 times 10 to minus 6. And shot by shot fluctuation is greatly improved like this, from the fluctuation of the 40% to about 4%, like this. And next, we check the delay time dependence on the continuum spectrum to confirm the generation of isolated attosecond pulse. These are the experimental results. Left is pump delay dependence. This is idler time pump delay dependence. For both cases, we could clearly observe the half-cycle oscillation, indicating the generation of isolated attosecond pulses. Okay, these are the pump laser CP dependence of the harmonics, and this figure D is calculation. This calculation well agreed with the experimental result. And finally, we have concluded that shaping of this value correspond to the pump signal and idler phase gives the maximum efficiency at this point. Okay, up to here, I have two slides. Up to here, I show generation of intense isolated attosecond pulse in the XUV region. Next, I show you how to extend the wavelength of this intense isolated attosecond pulse to the water wind region by using this synthesizer. In the previous study, our synthesizer used 800 nanometer radiation as a main pulse. But in this calculation, the combination is changed. In this calculation, we use 1.9 micron pulse as a main. And this is a synthesized electric field by mixing this three color with the intensity ratio like this. Of course, the generation of 1.9 micron with the high energy is difficult, but we already realized 100 millijoule plus 1.9 micron pulses. Okay, so by using this waveform, we have generated the high harmonics. Of course, this is just a simulation, which includes the strong field approximation and propagation effect. By focusing this high energy three color pulse to the gaseous target neon, interaction length is 60 millimeter with a pressure of 32 torr. We use loose focusing to phase match in the water region. Thanks to the phase matching, we have generated strong high harmonics in the water window region. By Fourier transformation, we have obtained 55 attosecond pulses indicated by this red line. By changing the focusing condition, we could extend the high harmonic energy to 500 EV region with a pulse duration of 71 attosecond. Anyway, this case, less than 100 attosecond pulse are directly obtained without attosharp compensation. This is very important because when we use a metal filter or something for compensating attosharp, it greatly reduces the intensity of attosecond pulse. We hope to realize such a high intensity attosecond pulse, which allow us the attosecond probe experiment. That means the soft X-ray probe experiment near future. Okay, this is a summary. And this is my collaborator. Thank you for your kind attention.
Thank you very much, Katsumi. It's an impressive power of attoseconds, which can convert microjoules to gigawatts. And with this attosecond technology, we theorists will be even more challenged with new coming experiments. Thank you. Now, it's my pleasure to introduce the next speaker, who will be Professor Himadri Chakraborty from Northwest Missouri University. And he is one of longtime collaborators and fellows of Steve Manson. And he will be talking about photoinduced ultrafast processes in atoms and Fullerenes. Thank you, Himadri.
Okay. Thank you very much. Just take this thing a little away. Okay, all right. So hello, everyone. Title of my story is the photo-induced ultrafast processes in atoms and molecules. I have divided this into 3 segments. Of course, the first bullet point is to talk a little bit about my collaboration with Steve Manson in photoelectron spectroscopy. We have done a lot of work on molecular C60, atom in C60, and even C60 and C240 Bachianian systems in the vapor phase. But I'm not going to talk about everything that we have done. Of course, we'll pick up a couple of features, and I will show you later. They are bearing in some of our time-resolved studies that I want to go in the next 2 bullet points. The second bullet point is looking at some of the stuff which I've been talking about in the previous or the couple of initial talks, the Wigner time delay studies to explain the time-resolved experiment in atomic argon, MTC60, and then we have made some predictions for end of Fullerenes system, argon at C60. And then finally, I hope I'll be able to save some time to talk about some ultrafast charge transfer and transient entrapment of photoexcited magnesium electrons in magnesium in C60. So let me start with the collaboration with Steve. And as I said, that I'm going to be talking about only the work that we have done in end of Fullerene molecules. Little bit about the method that we have used. Our ground state is the methodology is based on the standard density functional theory. We smear the Fullerene ion core into a classical gellium system, but then there are valence electrons from each carbon atom is collectivized together, and we of course treat the central atom exactly, and then we do cone sham, find the ground state structure. We use some fairly well-known exchange correlation functional. Those are the typical things you do to get your result accurate in density functional theory. And then we have seen abundance of atom Fullerene orbital hybridization in the ground state. And this is the point that I want to concentrate in my collaboration with Steve Manson. And I will show a couple of consequences of this atom Fullerene orbital hybridization, and then use some of those ideas to show how that helped us to explain some of our results in the time-resolved domain. We do photoionization, of course, so we need to treat the correlation, and we treat it in a linear response time-dependent density functional theory approach. It is not exactly solving the time-dependent cone sham equations, but rather we use it in a perturbative approach. So I don't want to go into the detail of the theory, but eventually, due to the correlation, due to the electron-electron interaction under the dipole field of the photon, we calculate something called the induced density, but then we have to put it in the form of some potential so that we can use it in the matrix element. And that is calculated through this induced density by integrating over the space using the Coulomb interactions and some exchange correlation induced density, and we find something called the induced potential, and that comes in the matrix element in the form of an operator, which encapsulates the entire information about the electron-electron correlation in the dipole field, where Z is the typical one-body operator, and delta V, which is the induced potential, contains the many-body effect of the interaction, and which is, of course, a complex quantity. When we will jump into the Wigner approach, of course, you all know now that this photo amplitude, which is a complex quantity, will have its phase, and the modulus square will be the strength, and the phase is the time. The energy derivative of the phase is connected through this famous Wigner formalism to the time delay, to the intrinsic time delay. So hybridization in PES, which is the photoelectron spectrum, that's one thing, my collaboration with Steve, that I'm going to talk about. Now, I have now worked with Steve in the time-dependent part of what I will be presenting here. And since Chris Greene and Ravi Rao has already talked about some of their recent papers, which came through the collaboration of Pranav Deshmukh, Steve, and their collaborators, and Anatoli, of course. So I'm not going to go into that. I want to quickly show Steve's a picture. I mean, working with Steve was awesome. I mean, Steve inspires a lot of enthusiasm and encouragement in whoever works with him. And I just dug out a picture of Steve a long time ago. And in my mind, this embodies Steve's confidence. I'm pretty sure Steve doesn't smoke tobacco pipe anymore. We have left that tobacco era a long time ago. But I still wanted to show this picture. So I have one more picture, which is very contemporary. So there are two things which comes in relation to this atom-Fullerene hybridization that we learned in my collaboration with Steve. One is the enhancement of the atomic signal, atomic photoionization signal when the atom is sitting inside the C60 shell. And another, something called a new creed of resonances that we predicted, which we called OJ-ICD, coherent hybrid resonances. And both of them are connected with, they have the underpinning of this atom and Fullerene hybridization. It was just for the heck of it, I was just looking into the number of publications I have with Steve in the same co-authorship. It's 39, and we are currently writing our 40th papers. So I thought that's quite awesome. And I didn't realize that this is the number until I did a count today because I have to prepare for this talk. Here's a contemporary picture. 5 years ago, this is Andalusia in Spain. This is right after we visited that Alhambra, that Arabian fortress. And then after that, we are having a lavish Andalusian dinner. Betty and Steve Manson, Steve in his usual jovial self. We were sitting in a wonderful place. I was just behind the lens. There was a window just right up front, and we were looking at Alhambra through this window. So that was a wonderful time we spent together 5 years ago. So super happy birthday, Steve. All right. So let's go back to the business. The first thing I wanted to talk about, which is related to this gigantic enhancement of the atomic photoionization when atom is sitting inside the C60, let me just show you a result. So this is xenon 5P, where this is the cross-section, xenon photoionization cross-section is a function of photon energy. And this is a plain, nice, steady cross-section. And then I also want to show you at the same time the empty C60 cross-section, which has this giant dipole resonance, which is sitting right here. And then there is another resonance, the plasmon resonance, which appears in the higher energy part, which is slightly weaker but flatter and broader. But then when xenon is sitting inside the C60, due to the coupling, due to this hybridization, the trapped atomic matrix element has its free atomic matrix element, and then you have this coupling term through which the hybridized part of the atomic wave function can reach out and siphon or suck in some of the oscillator strength from the plasmon. And so if you look at the 5P photoionization of xenon, where xenon is sitting inside C60, you can see this huge enhancement in this red line, pretty much sucking the strength from the plasmon. This was essentially a very gigantic enhancement in the atomic photoionization due to the coupling, dynamical coupling. So this was a paper which we published a long time ago in Physical Review Letters. The other thing we have learned, the other important thing I want to talk about is this OJ-ICD hybridization. Now, all of us know what an OJ resonance is. So if you have an inner shell electron which absorbs some laser light and it gets excited to excited state, but it doesn't still come out. It may not like to stay in the excited state. It can come back and fill in that hole. It can release some energy, and that energy can knock out one of the outer shell electrons. And since the outer shell continuum, since this excitation is embedded in the continuum of the outer shell, you see a auto-ionizing kind of Auger resonance. Now, if there is a dimer, if there are two system creating some kind of a dimer, you can have a photoexcitation in one member, but the inner shell photoexcitation, it can de-excite, release the energy, but that energy can migrate to the other member and knock out an electron from the other member, which is called the intercoulombic decay, or ICD. Now, if there is a hybridization, then something very interesting can take place. So if the outer electron is now hybrid, so this kind of resonances essentially comes from the discrete and continuum coupling, which shows into this integral. So if this, the continuum electron, which is coming out from the hybrid state, is hybridized, then this continuum channel wave function would also have some atomic property and some C60 property. Okay, so if I show you a schematic picture now, it will get much clearer to you. We call this hybrid electron these green two broken cookies, which are essentially the bonding hybrid. A part of it sitting in atomic region and the other part is sitting in the C60 region. And now if there is an inner shell excitation in the argon and this excited electron drops back down, then one energy would be released, and one part of the energy can go out and knock the cookie which is sitting on argon. So that would be essentially an Auger decay. Okay, but the other part of that energy can migrate to the other system and knock out the other part of the cookie, and that will be an ICD. But when you measure this electron which came out, that hybrid electron, it will coherently mixed, so there would be an Auger and ICD signal into that electron. And this is the new kind of resonance that we have learned and we have predicted. And just to quickly, and the same thing can happen on the C60 side. You can have a C60 electron excited, de-excitation. One half of the energy can do a C60 Auger, and the other half from the argon electron can also get out by some part of that energy, which migrated, and that will create a C60 to argon or any atom Auger ICD resonance. So these resonances will show in the continuum part, which is the PES. For electron spectroscopy. So I just want to quickly show you that two sets of resonances. I just want to take a look at the red and green lines, where the red line is the argon C60 anti-bonding electron photoionization spectrum, and the green line is argon plus C60 bonding part. You can see these big resonances, which are fairly strong. A, B, and C is the resonance hybrid Auger ICD of argon holes, and 1, 2, 3, 4 are resonance hybrid Auger ICD C60 holes decay. And so these are the two very important non-time resolved work that our group did with Steve, which will have some bearing in the next part of my talk real quick. So that comes from, so let me just quickly skip this slide. Here are some of the people who were also participated in this program. Now, the time resolved part of the spectrum where we did essentially this Wigner time delay. And we can do it because we have this linear response, time-dependent density functional theory amplitudes. We have to get the phase and look at the energy derivative of those phases. Now, there are a couple of different ways people can make this measurement. One is the interferometric approach, which is called the Rabbit approach, which is the reconstruction of attosecond beating by interference by two photon transitions. The Rabbit approach, in some way, complements the way Wigner's approach works. So in the Rabbit, what you do, you have a UV, XUV harmonics, the odd harmonics, and you can try to excite using this 21st, 23rd, 25th harmonic. I'm just throwing some of the numbers. you can excite from some of the initial electronic state. So the electrons had gone these 3 excited states due to 21st, 23rd, and 25th harmonic. And then you can bring in your, so this is pump, and you can bring in your probe laser now, which is an infrared laser, and you choose your probe laser with a certain time delay in such a way that that has the energy, which is half of the two harmonics. So what can happen is that the electron which is excited in by the 21st harmonic can absorb 1 IR and reach in the midway. That is one way to reach this energy. And the 23rd electron can release an energy and an IR and a photon and come down to the same point. So there are 2 channels by which the same energy can be attained. So there would be the interference of these 2 pathways. And that's how you get your sideband 22nd. And the same thing can happen between 23 and 25th. You get your sideband 24th. And you can measure the phases of this interference spectrum. And then you can essentially calculate the delay at the energy in between by using the difference equation. You take the difference between 24th sideband phase and 22nd sideband phase, and you divide it by the twice IR energy, which is very similar to what Wigner formalism shows. It's essentially the time derivative. It is difference equation to the differential equation. So the rabbit field has a wonderful similarity with the way the Wigner is done. And because the phases are subtracted out, much of the probe effect is gone here. It's also canceled out, not totally, but quite a bit of it. So therefore, it can mimic the Wigner situation in a way. We have done some calculation just to check how our LR-TDDFT works to explain some of the rabbit experiment. This was an experiment which was done on argon 3p. It was actually a photo recombination. It's just an time inverse photoionization near. Did you tell me something, Anatoli? How much time I have?
Let's to go.
Okay. So these are the experimental results, and you can see that our TDDFT phase, 3p phase near the Cooper minimum agreed fairly well with the experiment. And the delay also agreed fairly well. So that was a great success of our approach. And I can quickly show you how our result agreed with Anatoli's RPAE calculation. These blue stars are Anatoli's result. And this is, of course, 3s to 3p relative delay for argon. And barring some phase energy offset, it qualitatively agreed fairly well. We went ahead and did the same thing for these 2 hybrid electrons in argon in C60. And you don't have to worry about most of the graphs here except these 2 plots. So these are the phases for when argon inside C60, the hybrid 3p bonding and anti-bonding. Black is bonding and red is anti-bonding. And you can see that while the red is coming up with a 2 pi phase upshift, the black is coming down with a pi downshift. So the phase in some way is working here for these 2 hybrid electrons photoionization, like what will happen for a Newtonian collision. It's a nice way to look at it, that the momentum is conserved. If one colliding particle has some positive momentum, the other will have the equal amount of negative momentum, so the momentum is conserved. So the phase in some way is behaving exactly the same way when these 2 hybrid electrons is coming out. So in some way they are colliding in time. And that was a very interesting result that we got, this hybrid part of the Wigner spectrum. And these are the 2 people, Gopal Dixit, who is now in IIT Mumbai, and Lamine Majid. They worked in this collaboration together, and we got a physical review letters in 2013. Recently, this is unpublished. We have a result for C60 plasmonic photoemission looking at the time delay. And of course, this is a streaking experiment that you are comparing with our collaborators in Seefeld and Munich. This is unpublished. Here, the the probe pulse effect is taken into account by doing some Monte Carlo simulation over the intrinsic Wigner delay. The black line is our result, agreeing fairly well with the experiment over the plasmonics part of the C60 photo emission spectrum. How much time I got, Anatoli?
You have to finish right now. I'm sorry.
I have to finish right now?
Yes. Oh, just 30 seconds.
Just a minute. Is that okay?
Be considerate to others.
Yeah, okay. Okay, then, well, and let me just quickly tell you that just one slide. This is our latest work where we are looking at the photo excitation of magnesium inside C60. And here it is not ionizing, it is exciting, and then it is de-exciting by electron-phonon coupling. So magnesium is a very interesting situation. Magnesium 3s is right inside the band gap, and a pump photon can come and it can excite surgically to the magnesium 3p, and then 3p comes back down, creating essentially a charge transfer for from the magnesium to C60. And we can measure this spectrogram for the charge transfer by, so you scan the spectrum by pump, and you look at the population of various states by a probe absorbance. And this is a recent result, and I don't think I have enough time to explain this. But if someone would be interested, we can discuss further about it. This is the work which has been recently submitted to physical review letters. So since I'm out of time, let me just skip over this.
I think you have to stop. Oh, I'm really sorry. We have so many more speakers, and they come from different countries.
Right. So this is the acknowledgement slide, and thank you very much.
Okay. Thank you very much, Himadri. What I suggest, you ask the organizers to put your full presentation PowerPoint document on the web, and I'm sure people will be excited to see your results, and there will be ongoing discussions, and you will benefit from it.
Okay, thank you.
Just to continue, I'm terribly sorry, we're running out of time, and our next speaker, it's
I understand.
Introduce Klaus Bartschat, who is a longtime collaborator of mine, and he made a prominent mark in electron physics and more recently in photon physics. And today he will be talking about controlling multi-photon ionization with circular dichroism. Thank you, Klaus.
Thanks a lot, Anatoli. So everybody can see my screen, I guess?
Sure.
Are we looking? Okay, good. Well, let me first of all thank the organizers, especially Anatoli, for inviting me to participate in these festivities. So I have been thinking quite a bit about what should I talk about. And so I ultimately decided on this particular topic that you see here, and including also some pictures of where Drake University is in Des Moines. We are 6 hours behind, so it's getting late here. It's even getting more later in Atlanta, so it's going to be tough for some of us, but we'll see how it goes. So this work is really based on this topic. So there you see on which system I'm going to talk about, and that is oriented lithium atoms in the 2p state by circularly polarized laser radiation. And this was, for example, also presented at DEMOP, and I put here a link. David Atri-Schuller, who is one of my students, gave a beautiful presentation. He was an undergraduate, he just graduated. A little commercial, if he applies to any of your graduate programs, try to get this guy. Nicolas Duguay was my postdoc a couple of years ago. He did a lot of work on this, on the code that we're using for this particular project. And it's a joint collaboration with the group of Daniel Fischer and Roland Missouri. So in fact, we also submitted this one to PhysRev letters, and I would have thought by this stage I could say that it is accepted, but I think it's just the last bit. The editors have not notified us, so I can't say, but I'm willing to bet that it will be accepted for PhysRev letters any minute. So when you talk about lithium, of course, you want to, in an event that honors Steve, you wonder, does he know anything about lithium? And so I looked it up. You can also see here some of his distinguished collaborators. I'm not on this list, so again, I'm very honored to be asked to say something here. And so when you look at this list, you might think, yes, maybe, because there is some aspect here where he wrote a paper with now the unfortunately also late Tony Starras, whom we lost a little more than a year ago. And so he talks about S subshell, so that's good because lithium has also an L subshell. Then I looked at it and so where on earth here is lithium? So they did work on sodium, rubidium, potassium, cesium, nothing to be found, but I think he still knows it. But then let me show you one of the pictures of Steve that I have. This is about 10 years ago at the ICPIC in Belfast, the Carrick-a-Ree, the very famous rock somewhere in the Antrim coast. And as you can see, he's rushing back from this rock, and so, or to the rock. In fact, I don't know exactly, but I think he's rushing back. And maybe he wants to work on lithium. I mean, who knows, right? At that moment. So this is my connection to Steve. We have known each other for a long time, but never published a paper together. But talked a lot, like Greene said, you know, we talked a lot about various aspects of physics. So here's the overview of my talk, some motivation about this particular work. Since it is combined experimental and theoretical, I will give you a very brief summary of both of those. Of course, I know more about the theory than about the experiment, but I'll try my best. Then I'll show you some results and then some conclusion and outlook. So what's the motivation? Well, of course, we all know that there are chiral molecules, for example. Chirality is very interesting in many subjects. And it turns out that you can use circularly polarized light, which also exhibits a handedness to break the symmetry in its interaction with matter. And lithium is a very simple chiral system if you manage to somehow polarize or orient the orbital angular momentum of the valence electron. You know, of course, hydrogen would be even simpler, but lithium is very close to hydrogen. And so this is the idea, to bring this the lithium atoms into the excited 2p(m=1) state. So such a system can be really a benchmark for studying this chirality in general, because a system like this can, as I will try to demonstrate you now, be handled very accurately, both from an experimental point of view as well as a theoretical point of view. So a possible application of this is that you can actually produce in this way that I will show you in a minute, a spin polarized electron beam that has a near perfect degree of polarization, and you can switch the polarization within femtoseconds. So this is the time dependence of the whole thing. And such a source could have applications if you want to study, for example, ultrafast spin dynamics in magnetic domains. I don't know much about this, but that is one of the possible applications of something like this. So let me show you the scheme of the process. So this is the basic idea. They do it slightly different, but due to symmetry, this is the same, and it's easiest to explain over here. So what happens is that you take lithium in the ground state and put it into a trap that you run with circularly polarized light, and so you bring these guys into the 2p(m=1) state. Now you could do also the same thing with 2p(m=-1), but in a trap it's not so easy. But as I said, due to the symmetry, it's done slightly differently, but the physics is exactly the same. So I'll explain it over here. So we get over here. So we have now an oriented state, and now we hammer on this state with another laser, which is also circularly polarized light, polarized. And now you need 2 photons to get out. And it's just enough to get out, as I will show you, which is experimentally quite challenging. So if you go this way, so if the the pump laser or the trap laser and the probe laser have the same helicity, you get a very simple angular distribution, which is basically determined by the spherical harmonic Y33. If you did this the other way, or if you come in here and go with a probe laser of the opposite helicity, it's the same thing. You get a linear combination of these two, not necessarily with the same amplitude, so it depends on how exactly it goes. But the point is that you get a completely different angular distribution due to this effect of here having interference between these two possibilities. And so the observable that we are interested in is this so-called dichroism, which is basically the signal, whether it's angle differential, energy differential, or angle or energy integrated, basically the signal that you get with the same helicities of these two lasers or different ones. You subtract it and divide by the sum, and you get this dichroism. So how it is done experimentally? Well, these guys in Rolla have an atom trap. So basically, they can cool the lithium atoms to basically about 1 millikelvin in an all optical trap. The laser wavelength is tuned, of course, to this 2s to 2p transition, which is 671 nanometers in this case. And basically 93% of these 2p electrons can be brought into the m=1 state. So you still have a little bit left in your ground state, and that is not completely unimportant either. But it's very highly polarized, very oriented target. And then you use a probe laser. In this particular case, it has almost the same wavelengths, which again, I will point out, makes the experiment particularly challenging. It is a 65 femtosecond laser, 200 kilohertz repetition rate, 10 to the 12 watts per centimeter squared. So it's not the Attosecond gigawatt laser that we just heard about, but it is a fairly good laser system. And then they have a reaction microscope, and this reaction microscope can then measure the electron and the ion recoil momenta in coincidence and get all kinds of information that you would like, including this dichroism. So here is our apparatus, which in this particular case, the picture of COMET is one of the supercomputers that we are fortunate enough to have access to. You might say, why do they need a supercomputer for a calculation like that? And I will just show you in a minute why it's actually quite useful to have access to a machine, although the calculation is relatively simple, I should say. And this is in fact what we do. We solve the time-dependent Schrödinger equation. Ravi at the beginning of this session said that this can be done these days. Yes, it can be done. It can be done very accurately, actually. And for a system like lithium, at least for the parameters that we are interested in, it's very appropriate. But nevertheless, if you want to get a real quantitative comparison with experiment, you have to work a little bit harder than you might have envisioned originally. So for example, we really needed the excitation energies, everything up to about 1 milli-electron volts or better from this model potential that we use to describe the inner core. So it's not trivial, let me just say that. Also, if we deal with circularly polarized light, it's much more challenging than doing linearly polarized light. But again, people now know how to do this. So we just run the code, and then at the end of the pulse, we have a wave function, we project it to the appropriate continuum states, and everything is fine. And just believe me, if it doesn't work out, then it's not the numerics, it's some missing physics, potentially. So, and this is the point, if you really want to compare experiment with theory directly, you must account for a lot of little effects that can be quite important, because it's a realistic experiment, right? So that means you do not have a perfect detector. You do not have perfect angular or energy resolution, right? There is an angular acceptance of the detector out of the plane that you may or may not know too much about it. You have to figure out what the laser intensity really is as a function of time. Of course, you can put a little nice shape in there, but maybe the intensity distribution is not homogeneous over the focus. So once again, you have to know a lot about the experiment. And so for one particular calculation, set of parameters, it might not be too difficult, but we need to do many, many, many of these runs to actually put the results properly together to compare really with experiment. And when you do all of this, you get something like this. So this is brings me back to the title of my talk. How do we generate or distribute the energy? And you can see here, this is on the left is experiment, on the right is theory for two different peak laser wavelengths. And what you see is that life is completely different if you have the 2p co-rotating case. So both have the same helicity, or you have the counter-rotating case. So in one case you get this, and in another case you get that. So you see the peaks are different energies, and that has to do with an outer towns splitting in the co-rotating case. So you see the very different energy distributions and also the magnitudes. So the dichroism is substantial, right? You also get this really nice shoulder, and that has to do again with this outer town splitting that is only applicable in the co-rotating case. It doesn't apply to the other one, so you sort of don't get this. The other thing that is not completely unimportant is we actually get something from the 2s directly, 3-photon ionization of that, and you see this is a good case for experimentalists. Of course, by symmetry, and theory has this perfectly, there cannot be any effect, whether you have co-rotating or counter-rotating pulses. Experimentally, you see something, but this has to do with how accurate is your experiment, because you do not believe that there is a fundamental symmetry breaking here, right? So the fact that these two experimental results are so close to each other shows how accurate the experiment at the end of the day is. And you see this beautiful, really, agreement. I mean, it's not 100%, but it is very good, in my opinion, right? It also shows you that increasing the probe intensity doesn't change the results substantially, but the hump is now very nicely seen in the experiment and, of course, in the theory. And so the dichroism is in the ballpark of 60%. We can also do this, of course, for the momentum distributions. So once again, this is what comes out of the 2s, is beautifully, symmetric here, and you can see these rings, and this is, the correct energy. Then you can do it for the co-rotating case, for the counter-rotating case. Here, the experimental signal is much weaker, but nevertheless, I think there's a good relationship between theory and experiment. So let me just, what I forgot to say is look at these energies. This is not trivial. 200 milli-electron volts, 100 milli-electron volts electrons. I used to be an experimentalist, and those things can drive you nuts if you have to figure this out. And it's much easier theoretically, but experimentally, this is tough to handle those low energy electrons. And that already brings me to my conclusion. So Anatoli gave me the yellow card to be sure not to go over time. So here are my conclusions. We found definitely a very large circular dichroism. The physics, in case Steve is interested in, is this helicity-dependent outward town splitting. I think the agreement between theory and experiment is excellent, and that really gives confidence, I think, in both. But it required a very fruitful collaboration, a lot of communication between the groups to really say, how do we compare apples with apples and not just do some calculation and hope for the best. The problem is challenging, really experimentally, maybe more even than theoretically, due to the two wavelengths of the trap and the probe laser are very similar. Very low energy of the electrons certainly didn't make life any easier for these guys. We, the royal we, it's not me, guaranteed. I have two left hands when it comes to experiment. They are now basically working on modifying the experimental setup, so they want to use different wavelengths of the probe laser, and they want to set different combinations of laser polarizations. So, for example, using one circular, one linearly polarized light, and have all kinds of ideas. And already the first results are quite interesting or at least puzzling. So there are strong indications that low-order perturbation theory may fail much earlier than we would have originally expected, but I can't say much about that right now. But so stay tuned for updates. There's a lot more to come. And with that, I thank you for your attention, but not before I do this. And happy birthday, Steve, and all the best for many years to come. Thank you very much.
Thanks, Klaus. That was absolutely perfect timing. And I hope other speakers will take it as an example. Thank you. Wonderful results. And we wish you success with your PRL. Now,
thank you.
The next speaker will be recent PhD graduate, Sourav Banerjee. And he one of many, many students who benefited from Steve's guidance and supervision. And it's my great pleasure to introduce Sourav's talk. He is now from Indian Institute of Technology of Madras, Chennai, and he will be talking on Wigner time delay in photodetachment of negative ions. Thank you.
Thank you, Professor Kheifets. So I'll just share my screen. Is the screen visible, sir?
No, we don't see it yet.
Okay. I just stop sharing and I'll start the new sharing once again. If that works.
Hello.
Hello. Yes.
Sir, please click on share screen, which is available in the Zoom window in the mid of the screen. With the
yes.
green.
Yeah, the green one.
Yeah. Yeah.
So,
once you click on it, it will ask you. There will be a pop-up showing what to share. Click on complete desktop and then click on share. Okay. Yeah.
But
just hold on. Just hold on.
Okay.
No, it is not sharing. I think. Are you able to see the screen?
I can see the screen, and when I click on it, it says that please restart screen sharing as it has stopped unexpectedly, something like that.
Okay.
So,
stop it. Stop the screen sharing.
Yeah, just I do that. Stop sharing. Yes. So I have stopped sharing.
Click on entire desktop. Instead of a window, please select entire desktop.
Okay. So is it visible now?
No, just wait. Still, we are not able to see the screen. No, there is some problem. We are not able to see your screen.
But for me, it is showing you are sharing the screen. Let me. So I am sharing the entire desktop, and then it shows that you are screen sharing.
Started. It is showing screening has been started, but there is complete black color window is appearing.
Maybe Saurabh, can you try rejoining it? Sometimes that helps.
Okay, so I'll do that. Yeah.
Pranava, maybe we just, I can see that Eva Lindroth is with us. Maybe we can ask her and to give some time to Sourav to fix his technical problem. Otherwise, we just losing our time.
Yeah, I agree.
Eva, can you hear us?
If Eva is ready.
I saw
she may not be anticipating her talk at this time, so we have to
mute. But she maybe just joined in, but she's not ready to give us a talk.
Yeah, so
It's a little bit early, isn't Hans Jakob here? Because I mean,
yes, but we have a technical problem with one speaker, and we ask you kindly, maybe you're ready to give us a talk, and we just change the time slot in the program. Would it be possible?
It is, but I'm not the next speaker. I'm the next speaker. So Hans Jakob.
I understand, but Hans Jakob is not has not joined in. I can't. Oh, he is also here. Maybe I ask him. Like I ask him to unmute. He's not talking to us. That's the problem. He joined in, but he put his mic on mute, so I can't talk to him.
You can talk to him, but he can't talk to you.
He even give us a talk, but
yeah, shattered.
Okay, so our fellow conveners will be all convinced that would be a good solution. What do we think?
Hans Jakob is there. Hans Jakob, do you hear us?
Yes, I can hear you.
So are you ready with your talk? Because there was a little bit of technical problem, and the previous talk will be presented after your talk. So if you don't mind.
Yes, that's fine. I can start.
Okay,
that's good.
Some little change in our program, so, yeah. We'll have to fix his technical glitches. But in the meantime, our next speaker will be Professor Hans Jakob Worner from Technical School at Zurich, and he will be talking about attoseconds of X-ray spectroscopy in the gas and liquid phase. And he's one of the leading experimentalists in attosecond science, and experimentalist and serious outnumber experimentalist by a good factor of 10. So it's a rare occasion when we have a good experimentalist on our program. Thank you. Hans Jakob, are you ready to go?
Hello?
Yeah?
I think he got disconnected.
Yeah. Ava, are you ready as the next?
It would be Eva then.
Next speaker?
Maybe Eva will we just use this time slot, because we have a problem with Hans Jakob also.
Yeah, I noticed that, but okay. And then I need to, okay.
Sorry for this sort of misfortune, but this happens.
Okay, I'm trying to have breakfast at the same time. So, this is okay. Should I go ahead then, or is that what you want? I try to share my screen.
Okay, so if you can share your screen, that would be great. If it works, I will introduce. Okay, at least something works. So I'm sorry for this sudden change, another change in the program. So let me introduce Professor Eva Lindroth of Stockholm University in Sweden, and he will be talking about attosecond delays in photo emission. Thank you, Eva.
So now you see the screen. That's fine. Okay. Yes. So thanks a lot for the introduction. It's very, and good morning, I should say, because I just woke up. It's very unusual to have a talk at, now it's before 7 in the morning. But I understand that most of you are still awake since a long time. So I'm very happy to be able to participate in this nice celebration of Steve's very important birthday. So I have tried to remember when I first met Steve, and I think it was at X93, which took place in Hungary, in Debrecen, in Hungary. And I remember especially that he made a big impression on me because he came with not only with a Hungarian dictionary, but he had also studied Hungarian for some weeks before he came in order to be able to help us all to understand more about the country. And as you see on these pictures, we have met in many places. Unfortunately, no pictures from as early as the 90s. But we have met on a number of conferences all over the world. And very often we discussed a lot of interesting physics, but I also remember happy moments. And we had many discussions because we have had many subjects we are both interested in. For example, these inner shell transitions and so on, which we started with on X93, but then also resonances and negative ions, photodetachment, and now more recently photoionization delays. And the photoionization delays, one can look at that as a new possibility to study the phase shifts. And Steve, he started with phase shifts a long time ago. And I want especially to highlight this paper, which is from 1972. And I think this is Steve's second most cited paper, as what I could see when I looked at it now. And it's a very detailed account of phase shifts in a number of systems. The reason that Kennedy and Manson wrote this paper or that it was so interesting in phase shifts in 1972 was, of course, that they studied photoionization angle distribution. And there we have a very strong dependence on the phase shift. And but now we have a new possibility to study the phase shift, and that is what I want to talk about more today. And I'm especially interested in the so-called rabbit measurements, and that's a way to use the Attosecond interferometry in the following way. You have this train of attosecond pulses. If you look in the time domain, in the frequency domain, you have then a comb of frequencies of harmonics. And then you shine this on your system, but you do this together with the fundamental laser, the laser which was originally used to through the process of high harmonic generation to get the comb of harmonics. And then the following can happen. You can either absorb one of the harmonics and get a sharp line, or you can absorb another harmonic and get a sharp line. But since the laser is also there, you can also interact with the laser and either absorb or emit a laser, and in this way you end up at the same final state. And in this way you have a classical case where you start in a specific initial state and you end in a specific final state, but you have two paths to get there. And then of course you have interference, and if you now change the phases between the two light fields, then this signal, which is called the sideband, it varies, it is modulated. And this is how it looks in the spectrogram. Here you have the sideband with these modulations, and it's through these modulations that you can get information about the phase. And to calculate it, of course, you need the amplitude here, you need the amplitude here, and you take the this amplitude, the modulus square. And if you rewrite it, you can isolate the oscillating term, the term which gives the modulations like this, where you have the frequency of the laser, and then you have three terms which all have the dimension of time. And one is this delay between the two fields, which the experimentalist can control. Then you have delay between the different harmonics, which can be there and which you don't know, but if you do clever experiments, you can get rid of that. And then finally you have the atomic part, and this atomic part, that's the interesting part here. And then so already long time ago in the 40s and the 50s, people like Wigner and others, they understood that there is an interesting relation between phase and time. And one can think of just a particle which goes over a potential. And of course, classically, we can then easily, at least if it's a simple potential, calculate how much, with what time the particle which passes over the potential will be advanced or delayed. And if you then have quantum mechanics instead, you have, of course, a wave. And what happens with the wave when it passes over the potential is that it changes its wavelengths and you get a phase shift. And if you take the energy derivative of this phase, you also get the time. And if you have a simple potential like this, it's very simple to show that this is exactly the same type of time as you have in the classical case. It's a little bit more complicated in the Coulomb case, but that was what, for example, Wigner gave us information about. Now, if you think about the rabbit method, it is not really measuring this phase directly. I mean, the Wigner type of phase, that's like this. I mean, you have a photon, and it is like a fundamental process, just releasing the electron, and then you have the scattering phase, and that is the phase. This is the Wigner picture, so to say. In the rabbit case, you have this releasing photon, but you also have the probe field. And this probe field, that is the thing which can really, makes this a measurable quantity. So what you really have of the outgoing electron or the outgoing wave packet in the rabbit experiment, that is this Wigner phase plus an unknown phase, which we usually call the continuum phase because it's a transition in the continuum. And now one could have hoped that this is very small, but it happens not to be so small. But one can still hope that it's very often rather easy to calculate. And if you can calculate it or you can know it in some other way, then of course it's this quantity which is very interesting. And this is something which Stephen and his co-workers has been doing a lot during the last decade, perhaps. But what I want to talk about first is a little bit what is really the role of this photon. And this one can do by calculating the full process. So there is the amplitude for this and the amplitude for this, and analyze the result. And then one get this type of pictures. So what you have here is the difference between the atomic delay, the thing you really measure in the rabbit, and the Wigner delay, the sort of fundamental quantity. And this is as a function of the energy of the ejected electron. And what you see here is this result for two different atoms. So it's neon and argon, and in both cases it's the outermost electron. And you can see they really show exactly the same result. So this is a sort of very promising that it it looks like it's a rather universal, and then you can hope to understand it and be able to correct your other experiments or calculations with that. Here I show also the so-called analytical formula, the analytical formula, which holds very well for a little bit higher electron energies, but for the lowest ones there is a difference, but there's still this universal behavior. Okay, so now one can say that this is of course just two cases, and these are for light atoms and for the outermost electron. So let's go to a more complicated, perhaps more interesting case. And what you see here is a rather recent experiment from Anje's group in Lund. It shows rabbit measurements of a little bit different kind of xenon 4D. And when you make a 4D hole in xenon, then you get also shear electrons. So what you see here is a two-dimensional plot where you have the slow electrons on one axis and the fast electron on the other. And on this part of the picture, there is only the XUV, only the harmonic, the combo harmonics, and this is what you see here when you integrate it in one direction, the peaks from the harmonics. Here we have both the harmonics and the laser field, and then you see, in addition to the harmonics, these side bands. So these are the rabbit signal here. And in this experiment, the photoelectrons in the sideband, generated by the sideband, they are measured in coincidence with the shear electrons. And because of that, you can disentangle the photoelectrons coming from the different fine structure components. And since this is a rabbit measurement, we should here be able to say something about the time delay. So as most of you know, xenon, that's a very old story. Xenon 4D is a very old story. This is a picture from Uwe Becker, where you have showing the photoionization cross-section, where you have this giant resonance covering hundreds of EV and very strong photoionization resonance. And this, Stephen has worked with this also, but no, I don't show his result. But this is, at least I don't think it's his result, but anyhow. In the experiment, and when you calculate the photoionization directly, you just see one big peak like this. But there has been some recent revisiting of this system. For example, Robin Santra and his group a few years ago, they claimed that although this looks like one resonance, it's actually two resonances. And this study was done with complex rotation. So they didn't calculate the photoionization directly, they looked at the resonance structure. So this is, I agree with this. If you do complex rotation, you get non-relativistically, you get the two resonances. But if you do it relativistically, you actually get four resonances. So you can even give them with numbers. So you would say that the big resonance is one rather broad, 25 eV or so here, and one somewhere here, which is extremely broad. And then there are small resonances here, which you don't see in this picture. So now we are a little bit interested. Can you see this in some other way? And this, that you have these resonances of the other symmetry, that is something you have indications of. For example, if you look at the cross-section and take the ratio between the cross-section from 43.5 and 45.5, you get a very strongly modulated curve close to threshold. Actually, you get this curve. The minimum here is actually where one of these triplet resonances is. The non-relativistic ratio lies here, so it's what you expect from non-relativistic considerations. And so this is a strong modulation. And Stephen has also worked with this similar things, because a few years ago he looked at the beta parameters, also comparing 3.5 and 5.5, and showed that there was a strong difference. So there is actually very pronounced spin orbit effects here in this system. And if we now look at the atomic delay, it's an even stronger modulation. What you see here is the atomic delay, sort of that is the expected signal in the rabbit. And here you have the delay of the 4D 3/2 electrons, and here are the ones for the 4D 5/2. And the gray line shows the non-relativistic result. So it's a big difference, and this difference is like 100 attoseconds. So it's very strong. And these lines here shows actually where the resonance, the triplet D resonance is again. Since this is electron energy, it lies a little bit different for the two fine structure components, because they have different, I mean, since we put them on the electron energy here, they are excited here with different, or ejected with a little bit different photon energies. So, and this is actually, at least qualitatively, what they see in the experiment. You see here the one going up and the one which is at least intentionally going down. And also in the experiment, they see very clearly that there's close to threshold, there is a 100 attosecond difference between the two fine structure components. One way to look at this and to perhaps understand something more is to look at the Wigner distribution. So this is just one of the channels, the 4D 5/2 to 5F/2. But you see similar things, although not so clear, in the other channels. And so you have the time here. You relate time and energy. And what you see here on here at very low energy is a feature which lives for a long time. And that's really in agreement with this finding that we have this triplet type of resonances, which lives for a long time. And then here you have this bright part. That is this very broad sort of giant resonance, which lives just for tenths of attoseconds. With some imagination, you can perhaps also see that it's narrowing for higher energies, perhaps a sign that you really have two resonances, so that here this is a combination of two singlet P resonances, because you have both the slightly less broad one and the very broad one, and here you have only the broad one. So I think this is a nice example that perhaps that with these new techniques, one will be able to disentangle more effects which are more hidden in the usual ways we have to study. We have been able to study resonances, for example. This is now generated by the theoretical results, but it's possible to generate similar pictures if you have good data also from experimental data.
Yeah, so, you have 3 more minutes to go.
One.
Okay, that's better.
Yeah, I just have this is my last slide. So and I wanted to finish off with showing this again, coming back to the question about the universality of the CC delay, and now just for this case here with the 4D. So this is the Wigner delay is the gray ones for the two fine structure component, and then we have the blue one, which is the atomic delay. And so the difference is here, the red. And here in the dashed line is the analytical curve. And you can see it agrees well when it's for higher energies, highest here, 10 eV or so. But at very close to threshold, there is really a difference. So here you cannot rely on just this simple universality idea. my conclusion is that this here we can see in this system in the rabbit measurement a clear difference for the fine structure component, and we can also see that this time frequency analysis can show us more details and show how the fast decay of the giant dipole is accompanied by a slow delay, and this slow delay involves a spin flip. This is just acknowledgement to people who has been participating, especially Michael Stahlström, and then the Anne Huyes group who made the nice experiments. And finally, I just want to say happy birthday, and I hope this bad times with viruses is soon over and we can soon meet again. Thank you.
Thank you very much, Eva. You saved us by filling this time slot, and it's a wonderful talk. Thank you. Now we have to decide which way we go. Who is the next speaker? Is Sourav ready to go, or?
Yes, sir. I can try to share the screen now. I hope it works this time.
Let us try one more time. If it doesn't work, then we'll find some other way to present it. Okay, now it works.
Okay. Yes, is it visible, sir? No?
Yeah, okay.
So a very good morning from India to all the attendees from different parts of the world. First of all, I would like to thank the organizers for giving me the opportunity to show some results on the Wigner time delay in photo detachment for negative ions. I take this opportunity to wish a very happy birthday to Professor Manson, with whom I got a chance to work with during last few years of my PhD program. It has always been a very wonderful experience to meet him and work with him, and I wish to learn a lot more from him in future. So now coming to the topic of my talk. So as we know that when a free particle interacts with a potential, it experiences a phase shift. And this phase, so where I have written like the ingoing wave and the outgoing wave. So you can see that there is a extra phase shift here. This phase has all the information about the potential. Now time delay is defined as the energy derivative of the phase shift. So this idea of a time delay in quantum scattering was introduced by Eisenwood and Wigner first, and then later by Smith. And this is defined, as I said, like the energy derivative of the phase shift here. So we call it Wigner-Eisenwood-Smith time delay or the Wigner time delay. Now photoionization occurs when a photon of sufficient energy knocks out an electron and the residual is a positively charged ion. So here all the information about the process is contained in the transition matrix element, which is a complex number. So it has a magnitude and a phase. And there are several parameters that we can measure in experiment. So those are cross sections, angular asymmetry, and spin polarization. And the recent addition to that is the time delay. So these things give some idea about the transition matrix basically. So now moving to the next. So as this figure shows that photoionization and scattering has different initial states, but it has the same final state. And these two processes are related by time reversal symmetry. So the idea of this time delay can also be applied to the photoionization case. Only the difference is that the electron exists in the exit channel for photoionization. There is no electron in the entrance channel here. So it is also referred, like photoionization is also referred as half scattering process often. And therefore the time delay in photoionization is half of that in the case of scattering. So if we can somehow get to the matrix element, then the energy derivative of the phase of the matrix element will give us the time delay for photoionization. Now in the case of photodetachment, there is only one difference with photoionization, that the residual thing is a neutral atom in this case. And that's why the escaping electron doesn't see any Coulomb interaction. So this electron is loosely bound to the target initially when it is a negative ion. by polarization potential. And these photodetachment processes are like very important to study many electron correlations near the low kinetic energy of electrons, because as I said that these electron correlations are not screened by the Coulomb potential, long range Coulomb potential. Now the available experimental techniques that we have today is the Rabbit and Attosecond streaking, and the measured time delay in both of these experiments have two components. One is the intrinsic time delay, that is due to one photon transition, so which we call Wigner time delay, and there is another time delay component which comes due to the measurement technique. So it is called the continuum transition for Rabbit, or the Coulomb laser coupling for Attosecond streaking. Now, as I mentioned, that there is no Coulomb interaction present, since the residual is an atom, neutral atom here in the case of photodetachment. So tau Cc vanishes and we are left with the Wigner component only. So these are the results I have taken from a publication by Professor Lindroth, who just talked about the Attosecond time delay. And here the authors have shown that compared the results of the photodetachment with the photoionization. So if you look at the right panel, so these are the photodetachment results for fluorine minus and chlorine minus. And at the left panel, we have neon and argon, which are isoelectronic with fluorine minus and chlorine minus. So if you look at the red dashed curves, so you can see that this is the tau Cc part, which is very similar in both the photoionization case, and it shows a substantial negative delay even at higher photon electron kinetic energies. But in the case of in the case of fluorine minus or chlorine minus, it shows that it vanishes. It shows that tau Cc vanishes just after a few eV. So, but there is another point that they showed in this paper, that the delay very near to threshold is having almost same value. So it is almost like species independent in both the cases. So kind of universal, because it is due to the Coulomb phase, which is dominating in this case. But here very near to threshold, the value for the time delay in case of fluorine minus is very different than fluorine minus. So it goes to 60 attosecond for fluorine, and then almost like 30 or 35 attosecond for fluorine minus. So it is different. So it is kind of non-universal in the case of photodetachment. Now our main aim will be to look at the Wigner time delay component in photodetachment for some of the atomic negative ion photodetachments. So we have taken some of the closed shell ions for study, and I have taken specific examples for chlorine, iodine, and lithium for this talk. So as you can see, this middle column shows the employed relativistic formalisms, many-body formalisms that have been used for the calculation here. So for chlorine and iodine, we have used RRP and RRPR respectively, and for lithium, we have used RMCTD. So these techniques have been employed as per the presence of important electron correlations in these specific cases as mentioned in the literature. So I will come to this lithium minus, and I will talk a little bit about MCTD, why it has been employed here. So these results for the chlorine minus are already published results, and we have some results which I will show for iodine minus, which are preliminary results. And unfortunately, I don't have the result for lithium minus yet. We are still working on that. But as I said, I will mention why it is interesting to study. So here, the top panel shows the cross section for the photodetachment of chlorine minus 3p, and the lower panel shows the result for the photoionization cross section for argon, again for the 3p. These are isoelectronic systems. So as you can see that both of these systems, like chlorine minus and argon, has a delayed maxima or safe resonance. And they have, if you look at the matrix elements here, you can see that there is like a Cooper minima around 50 eV for both of these cases. These results are also shown by Professor Rao already at the beginning of the session. So another fact here is that the chlorine minus photodetachment cross section starts from 0 because of the Wigner threshold law. So as I mentioned that there are two structures like the safe resonance and the Cooper minima here. So you can see that for chlorine minus and argon, in both the cases, the phase, so these are the upper panel shows the phase for chlorine and argon, and the lower panel shows the time delay results. So as you can see, around 40 to 50 eV, there is a sharp jump in the phase, pi jump in the phase. This is due to the presence of Cooper minima. But if you look at the near threshold behavior, so you can see that the P2D phase first goes down and then it goes up. So this is a typical behavior for the safe resonance, which is completely missing in the case of argon because the Coulomb phase dominates near the threshold here. So it doesn't actually, this safe resonance doesn't really show up in this case. So here, if you look at the time delay again, the time delay goes negative for chlorine minus, but it is highly positive for the argon because again the dominance of the Coulomb phase. Another interesting fact here is that if you look at the near 3s threshold, we can see a Wigner cusp kind of structure, which is not observed in the phase. Of course, it is there, but it shows that the time delay is like more sensitive probe to study this kind of feature. This work is also like done with the collaboration with Professor Kheifets and of course with Steve Manson. And so here we show the angle dependence of the chlorine minus and the argon again. So if you look at the near threshold behavior, chlorine minus shows that there is a very nice angle dependence coming into the picture, but it is completely missing in argon. So the reason for this is that L to L minus 1 means the P to S transition here dominates because of the Wigner threshold again, dominates near the threshold, and then P to D takes over. So there is a competition between these two channels, P to S and P to D, and this essentially comes shows the angle dependence. But in the case of argon, as I mentioned, that the Coulomb phase dominates, so all other many electron correlation effects very near to threshold is shielded by the Coulomb field, and it shows a positive time delay again. So there is no angle dependence. The another feature is that since there is a Cooper minima lying around this region, so there is a nice angle dependence again coming for chlorine minus and argon, both the cases. So now we look at the same chlorine minus 3p cross section, but at the region of 2p threshold. So it is far above the threshold of 3p, but we wanted to look at the effect of 2p on the 3p. So here, as you can see, that the 3p cross section is almost 10 times lesser than the 2p cross section. So 2p influences the 3p channels in this region. So here, as you can see, that the partial cross section for 3p shows a significant change due to the interchannel coupling with 2p. So the black curve shows only the 3p. If we would have not coupled the channels from the 2p, but when we couple it, we can see there is a large deviation from the monotonically decreasing curve. So this actually affects. Now we look at the same effect on phase and the time delay. So if you can see that 3p half and 3p 3 half, both of them show significant change there for the 3p. Again, the red curve shows that, and on the time delay curve also you can see that there is a significant change coming due to the interchannel coupling here. But the important point also to notice here is that this time delay behavior for 3p half and 3p 3 half are very different. So since these are spin orbit split channels, so this is attributed to the relativistic effect. So we can actually say that the relativistic effect is important to consider here. Now I come to the iodine minus result. So this is a recent result and we are still analyzing it, but I wanted to show the iodine minus result for different subsets like 5A, 5P, 5S and 4D. So here, as you can see, that these solid curves are the results for higher spin orbit coupled angular momentum channel, and the dotted are the lower spin orbit angular momentum number. So there is a difference between again the P3 half and P half in these cases, and here for D also it is same. So we can again attribute this to the relativistic prominent relativistic effect, and the different colors show the time delay for different angles. So you can see that there is a nice variation also with the angle. Now the feature which is coming very near to the 30 eV around this region is because that 5P has a Cooper minima around this 55 eV region. So there is a significant change coming into the picture. And then for here around 160, this is also another Cooper minima. This is the second Cooper minimum, which comes because of the interchannel coupling with the 4D channels here. So it is also showing its effect here. So for the 4D, we can see also that there is a significant angular dependence coming into the picture. Now, if you look at the 5S, so there is a structure coming here means in all the curves it is there, but for the blue curve it is very prominent. So it is because the 4D channels are opening around 50 eV. So here if you look, it is also around 50 eV. So this is also having some interchannel coupling here with the 5S, and this shows its effect. So we can see nice angle dependence, the relativistic effect, as well as the interchannel coupling effect for this result as well. Now for the like as I mentioned that I wanted to mention why the lithium minus will be an interesting case to study, is that if you look at the cross section for lithium minus or even sodium minus, so you see a Wigner cusp kind of feature very near to the first excitation threshold. So this is the 2s cross section, but if you look at very near to the 2p excitation threshold, so there is a Wigner cusp, and to get that we have coupled 8 configurations in the initial state, and there are like 20 channels in the final configuration, which I have not shown here. But the important point to look at is that the first configuration 1s2, 1s2, 2s2 is having a photo detachment channel. So 2s electron ionize, photo detaches, and then the second configuration which is 1s2, 2p half, or the third configuration which is 1s2, 2p 3 half. This goes to some higher excited state. So it all this happens because there is a photo detachment channel from 2s and a photo excitation from the 2p configuration. So due to the interchannel coupling between the photo detachment channel and the excitation channel, there is a kind of cusp behavior which is coming into the picture. And time delay will of course show some behavior here. So we have employed the MCTD technique because it allows us to take excited bound states into the configuration which RRPA or RRPR doesn't allow us to do. So that's why we have taken MCTD, and you can see that MCTD results already reported before shows the kind of this behavior. So not quantitatively, but at least qualitatively, it shows that there is a cusp kind of feature coming into the picture. So we have taken up this this case to study time delay, and I will like to name a few other members of our group who helped me with the results and also working in the same project. So Dr. R.T. Ganeshan, who helped me, like who's helping me with the lithium results, and Jobin also is helping me. And the chlorine results that I showed is from Somojit's publication. So those are the results that we have got in recent times. So yeah, so these are the results I wanted to show as a general study of the photo detachment that we have been pursuing recently. So yeah, so thank you for your attention.
Thank you very much, Sourav. A wonderful talk. And finally, our last speaker, Professor Hans Jakob Worner, and let me introduce him again. It's Technical University Zurich, and he will be talking about attosecond soft X-ray spectroscopy in the gas and liquid phase. And we apologize for disruption of his talk, but he has a prize of uninterrupted talk because he's last in the program. So I won't stop this talk.
Thank you very much, Anatoli, for the kind introduction. And I would indeed like to apologize to everyone for the technical problem. So it's a really great pleasure and an honor to contribute to this online symposium. And let me in particular wish very happy birthday to Steve and wish him many more years of happiness and scientific excitement. So today I will be talking about some recent attosecond experiments that we have done, the main goal of which is to advance attosecond spectroscopy in molecular science on one hand, but also to advance it into the liquid phase in order to study chemical problems that play a role in chemical reactivity. So I will split this talk in two parts. The first part is about measuring attosecond charge migration and observing the decoherence and revival caused by nuclear motion using transient absorption spectroscopy. And in the second part, I will discuss photoionization delays, about which we have heard wonderful talks already, discussing molecules, liquids, and also clusters as a bridge between the two phases of matter. So the topic of charge migration is, of course, a central one in attosecond chemistry, and there have been beautiful predictions. Whenever ionization creates a superposition of electronic states, there is charge migration. This can be caused by electron correlation, or it can also be caused by ionization by a broadband pulse. There have been beautiful experiments on amino acids by the Milano group. And also a few years ago, we have reconstructed charge migration in a small molecule from high harmonic spectroscopy. So the strength of high harmonic spectroscopy is its ability to resolve very short time intervals down to a few tens of attoseconds. But also the window of observation is limited. And so while we were able to observe this charge migration in the first 2 femtoseconds in the iodoacetylene cation, we were not able to observe the further evolution, and in particular, the effect that nuclear motion has on attosecond charge migration. And so this has been a strong motivation since, and we have continued in the development of experimental techniques. And I will now discuss very recent results where we observe charge migration in a neutral molecule, namely silane SiH4, using strong field pumping by a few cycle infrared pulse and transient absorption by an isolated soft X-ray pulse. So this is the schematic setup of the experiment. It's a typical attosecond transient absorption experiment that we carried out in this case at the silicon LH. So this is a scheme of the experimental conditions. We have used a few cycle pulse to create a superposition of electronic states in the silane molecule. In this case, it's a superposition of a low-lying valence state and a low-lying Rydberg state. So the pump pulse creates this superposition in the neutral molecule. It also ionizes to some extent, but the signature of SiH4+, which dissociates to SiH3+ entirely, is separated from the signal of the neutral molecule that we observe here, just below the LH. The dynamics is then probed by transient absorption, giving rise to a static absorption spectrum that can be separated in a valence region and a Rydberg region. And here in the differential absorption signal, we observe oscillations with a period of 1.3 femtoseconds. And these oscillations, they decay rapidly during the first 10 femtoseconds, as can be seen here. So you can see intensity oscillations that decay. And then after about 40 femtoseconds, these oscillations revive. And so here you can again see 1.3 femtosecond oscillations, 40 femtoseconds after the pump pulse. And these oscillations, as I will convince you in the next slides, are due to charge migration or a coherent superposition of electronic states in the neutral silane molecule. So what we see here is the decoherence and the revival of an attosecond electronic wave packet in silane. So by doing a Fourier transform over the experimental data, we can assign the states that contribute to it. This map here shows the Fourier transform line by line of the attosecond transient absorption data. The horizontal axis is photon energy, and the vertical axis is Fourier frequency. And so we can find now distinct peaks around 0.72 petahertz, which correspond to this valence Rydberg coherent superposition state. It can be assigned to individual states in the Rydberg manifold, and then we can find the coherent partners in the valence region that correspond to this characteristic beating. So there is one dominant group of coherences here, which is the one that is prepared by the pump pulse directly. And there is a second group of coherences at slightly higher frequency. And these correspond to a superposition between a Rydberg state and a dark state in the valence region that is only populated by non-adiabatic population transfer. So to show this, I have here the level diagram. So the lower coherence here corresponds to the B state in the valence region being coherently prepared with the C state in the Rydberg region. And this lower frequency corresponds to a coherence between a dark state, that we call the A state, together with the C state. And initially, we prepared a coherent superposition of B and C by the pump pulse. And at a later time, this coherence is transferred to AC through non-adiabatic coupling. So this is an overview of the experimental data. Here in black, we see the oscillation measured in the differential absorption signal that decays in about 10 femtosecond and then revives around between 40 and 50 femtosecond. And this is being compared to calculations of the electronic coherence between the B and C states in purple and between the A-C states in blue. So these are calculations done by the group of Alexander Kulev using multi-configurational time-dependent Hartree methods. And they indeed support the interpretation that the electronic coherence created by the pump pulse decays in 10 femtosecond, revives around 50 femtosecond, and a part of the coherence is also being transferred to this AC pair of states. Now, from these results, we can also reconstruct the time-dependent electron densities, for example, around the revival here, where the BC coherent dominates. And the BC charge migration corresponds to a superposition of the 4A1 valence state and the 5S Rydberg state. And therefore, it corresponds to radial charge migration, because these are essentially the 4s and 5s atomic orbitals of silicon that are being prepared. And this leads to charge migration along the radial direction, as can be seen by these differential electron density plots here that are shown in steps of about 200 attoseconds. So this is half a period of the charge migration that corresponds to a time interval of 690 attoseconds. So what is the origin of this dephasing and revival? So it is due to nuclear motion in these different states. So the pump pulse creates a superposition of the Rydberg state in red and the valence state in purple. But as you can see, they have different potential energy surfaces. And so there is nuclear motion here that takes place on different time scales in these two states, leading to autocorrelation functions shown on the left here that lose overlap as a function of time. And then after about 50 femtosecond, they regain overlap in coordinate space and in momentum space, leading to the revival around 50 femtoseconds. So this revival is due to adiabatic nuclear motion in these two electronic states. But what is even more interesting is the transfer of coherence from the bright purple state to the dark blue state. And this is caused by conical intersections, or in this case, a pseudo-Jahn-Teller effect between the B and the A state, which causes transfer of population from B to A within a very short time, about 7 femtoseconds. And this is short enough that also the coherence, the electronic coherence, is being transferred from the initially prepared BC superposition state to this AC superposition state. And this gives rise to the coherence shown in blue, observed also in the Fourier transform. And this corresponds to a different type of charge migration, namely it corresponds to angular charge migration, because the the dark valence state, the A state, has a 3T2 excited state orbital. And that, of course, superimposed with the 5s Rydberg state gives rise to radial charge migration, as shown in these reconstructed electron density plots. So this shows that electronic coherence can be transferred through conical intersections and leads to a transfer of a change of charge migration in its spatial character. Now, from this, we can also reconstruct the time-dependent density over the whole interval that was measured. So at the early time, we observe a very strong electronic coherence that leads to a purely radial charge migration. The amplitude then decays over time. Here around 20 to 30 femtosecond, there is not much change, but then we observe this revival, and this revival starts with first mainly angular character of the charge migration, and then it again develops a radial component to the charge migration due to the revival of the main electronic coherence. And so these measurements show that nuclear motion can strongly modify charge migration, and also that electronic coherence can be transferred from one pair of states to different pair of states through conical intersections in molecules. Now, in the second part, I would like to briefly talk about a few recent results on photoionization delays. So previous talks have given a wonderful presentation of what these delays are and how they are measured. So I will be very brief, and I will just mention a few steps that we have taken to measure time delays in molecules, and then in the liquid phase, that is a very recent result. And in order to better understand this very complex step from isolated molecules to the liquids, I will briefly discuss some results that we have obtained on water clusters as an attempt to bridge this gap between the gas phase and the liquid phase in photoionization dynamics. So this is data taken from an article published in 2016 on photoionization delays in molecules. This is a measurement done on the isolated water molecule in the gas phase, where we extracted a time delay of 10 attoseconds between photoelectrons associated with the ground state and the first excited state of the H2O plus cation. So these delays are small compared to another measurement that we did on N2O. In the case of N2O, these delays amount to 35 attoseconds. And this is done at a particular photon energy corresponding to sideband 14. Now, in this work, we repeated the measurements at different photon energies, and we found that the delays are always relatively small in H2O, but in N2O, there is a local maximum around the photon energy of 30 eV. And this is in quite good agreement with theoretical calculations that we did based on electron molecule scattering theory, so ePolyscat in particular, developed by Robert Lucchese. And this allowed us to obtain a reasonable agreement between the calculations and the experimental data. And this analysis also showed that the large local maximum here, as you can expect, is due to a shape resonance. And these photoionization delays, they are closely related to the lifetime of this shape resonance. Namely, in our calculations, this shape resonance has a lifetime of 110 attoseconds. And in the experiment, the delays are slightly larger, suggesting that the lifetime is in reality a little bit longer. And I want to point out that this work has greatly benefited from interactions with Steve Manson at Gordon conferences and also at DayMOP, where he encouraged us to study this and also to look at Cooper minima and the signature of Cooper minima in time delays in molecules. And this is indeed work that is still ongoing in our group at the moment. This is work done on isolated molecules. From here, we were interested to understand whether these methods and idea can be extended to the liquid phase. And to do these measurements, we combined a liquid microjet to study liquid water. And we applied attosecond interferometry, so Rabbit, in order to measure time delays, in this case, between liquid water in the jet and the evaporating gas phase, where we have isolated molecules. And in this work that I will not discuss in detail, we were able to extract the time delay between oscillations that originate from liquid phase water and the oscillations that originate from the gas phase water. And we found that these time delays, they are always positive, and they are small. They are on the order of 70 to 50 attoseconds at the 2 photon energies that we studied. And of course, there can be a lot of contributions to these delays. But the main contributions that can occur are from the direct environment of the water molecule, which causes a change in the electronic structure of the molecule and the photoemission delays, and possibly also from electron scattering as the electron is being transported out of the liquid phase. And so to understand this, we did quite detailed calculations using the same method as I described before. And we found that indeed the main effect in these experiments comes from the direct environment of the water molecule. So when we calculate delays for the isolated water molecule, we find that they are 50 attoseconds or 18 attoseconds. As we add one solvation shell, the delays increase. As we add a second solvation shell, they still increase a little bit, but much less. And finally, we can now take the difference of the delays between these largest clusters and the monomer, and we find delays that are in very close agreement with the experimental data. So this calculation suggests that the main effect of the delays comes from the direct environment of the water molecules. And we additionally did some detailed calculations to understand the effect of electron scattering on the time delays. And using Monte Carlo methods that I will not have time to describe, we found that indeed laser-assisted electron scattering plays a role, but it does not contribute to the measured delays, or that the contributions are very, very small on these time scales. And this allows us to conclude that indeed the time delays mainly reflect the effect of solvation on the water molecules. So by measuring time delay in liquid water, we mainly probe the effect of the environment on the electronic structure and the scattering dynamics during photoionization step in the liquid phase. Now, of course, this is a big step from the molecules to the liquid phase. And there is an important intermediate step one can take, and this is to study water clusters, because this allows us to understand how the photoionization dynamics evolves from the isolated molecule to the liquid phase. And to do this, we performed a rabbit experiment in a cold trims spectrometer. So we are able to measure the size-resolved water clusters and to measure in coincidence a rabbit trace for each of these water cluster sizes. And this allows us now to extract time delays between water clusters and monomers as a function of the size of the water cluster. This works because when we measure the mass spectrum, we see protonated clusters, and we know that up to about 10 water molecules, there is a unique relation between the protonated water clusters and the parent neutral cluster, because it is dominated entirely by single OH loss. So there is a direct relationship that allows us to associate time delays to well-defined cluster sizes. And so these are the results. We find that the time delays relative to the monomer, they increase almost linearly up to the tetramer, and then they saturate. There is no further evolution. The large symbols are experiment, the small symbols are the theory. And now the interesting question is, why is there an increase and a saturation? And this has a surprisingly simple explanation, namely this linear increase here can be shown to arise from the delocalization of the electron hole. So this is the monomer, this is the dimer, and you can see that in the dimer there are two orbitals. One is localized on one molecule only, and the other is delocalized. And with increasing degree of delocalization, the time delays increase continuously. And now one can wonder why is there saturation here? And this saturation is due to the fact that the electron hole delocalization in the clusters does not increase further beyond the tetramer, because the tetramer has, because of its high symmetry, it has full delocalization of the electron hole. But the larger clusters, they have, because they have low symmetry, they have a partial relocalization of the electron hole, and the electron hole remains essentially constant in size upwards from the pentamer. And these spatial extension of the electron hole is essentially similar to that in liquid water. And of course, this was a qualitative explanation, but now we can plot the measured time delays as a function of the first moment of the electron hole density. So this is a quantitative measure of the electron hole delocalization. And indeed, we find a very nicely linear relationship between this time delay and the first moment of the electron density up to the pentamer. And then from the pentamer to the hexamer and the heptamer, we see only small increases, which are due to intracluster scattering effects. So what we have found here is that there is a direct relationship between time delays and electron hole delocalization. And the localization effect that we see in the larger clusters, this is similar to Anderson localization, because in solids, the loss of translation symmetry leads to a localization of the electron wave functions. And in the same way, the loss of symmetry in going from small clusters to bulk liquid water is caused to disorder. And this leads to a localization of the electron hole that apparently is mapped quite directly into the attosecond photoionization delays. And this suggests, of course, using attosecond time delays as a way to probe disorder-induced hole localization, not only in liquids, but perhaps also in solids and in complex materials. So with this, I want to close. I want to thank the people who did the work, also in particular our collaborators on the theory part of the silane work. And I want to thank you very much for your kind attention.
Thank you very much, Hans Jakob. We conclude our session on really high note, and you give us beautiful prospects for attosecond science towards the future. And let me, with all of you, to thank our speakers for our wonderful session. And we also want to say something nice to Steve Manson, and that who gave us the reason to organize this workshop. Thank you, and happy birthday to Steve.
Thank you.
Thank you, Anatoli. I think this was a great session, very nice talks. There are, I think, a couple of questions in the chat box.
I will those. I recorded these questions. And
yes.
And I will just forward them to the speakers.
Yes, right. Right, and then the speakers could respond to them either now or maybe respond later.
Some of the questions are already answered.
Yes, yes.
So, actually, quite.
Yes.
And everyone on the East Coast, last call is in 6 minutes.
That's right. Everyone on the East Coast is sleepy.
Yeah. I think we should just end the session and let them go to bed because it's really late on the East Coast. And thank you all very much. We will meet for the session 3, which will be Thursday early morning in India and various timings in various other towns all over the world. It will be Wednesday afternoon in the US. And in Australia, it will be around dawn or very early morning. So,
I can deal with early afternoon.
Yeah. And that gives us a free day today.
Yes, sort of. Yes, sort of. All right. So thank you all very much, and we will meet. We will meet at session 3. Alfred will be chairing that. So goodbye, everybody.
Thank you all.
Take care.
Goodbye.
Good night, good morning, as the case may be.
Hey, Ravi, I was going to ask you a question. I'll talk to you later on.